So I'm excited to welcome you guys to the OHDSI community and learning more. I think this is a great way to prepare for tomorrow's talk, especially if you're new to the community. This is going to kind of give you an overview of kind of the main things that you need to know about within the community. It will make listening tomorrow a lot easier. So this is the introduction to the journey from data to evidence using OHDSI. So today, what we will walk you through is how do we go all the way from raw data in medical records or billing systems all the way to actually generating evidence. And over the course of the day, we're going to talk about the tools, the best practices, and our open science approach to doing that. And by the end of this lecture, what I hope is at least you're exposed to all the main content so that you can start to understand, hey, maybe I'm interested in open source development, or maybe I'm interested in thinking about the common data model. And so you'll at least kind of know all the main parts. As we get started, I want to introduce you to today's faculty so you know a little bit more about who we are. So I'll start with Mui Van Zandt. Mui works at IQVIA, and I would say Mui played a pivotal role at IQVIA helping them transform their data assets into the OMOP common data model. Mui is a very active member in our community, and I would say she's also very important in the Asia-Pac community. I would say she helped get that started, and as well as helps continue to drive moving that community forward. Okay. But today, Mui is going to be talking to us about data standardization. Linyin Zhang is an assistant professor of biostatistics at Washington University School of Medicine in St. Louis. Her journey with OHDSI started about 6 years ago when she was getting her PhD at Columbia University. She is an expert on causal research, and so she's going to teach today us a little bit about the methods that are core to OHDSI. Jenna Reps works at Johnson & Johnson. She's also an assistant professor at Erasmus Medical Center. Jenna has a background in mathematics and computer science, and so that has led to her ability to help develop the patient-level prediction package that the community uses. Not only that, she helps support a lot of different packages within the community, and so it only makes sense that today Jenna is going to talk a little bit about open source development within the community. Danny Pareto Alhambra is a professor of pharmaco and device epidemiology at the University of Oxford. He is also a professor at Erasmus Medical Center and the deputy director of the Darwin EU, which you'll probably hear a little bit more about Darwin over the next day or so. I would say Danny has played a pivotal role within the community of helping us think about how to design, conduct, and interpret clinical research. And so today, his part of the lecture will do just that. He'll help us look through and look, once we've generated evidence, how do we actually interpret it? And myself, I'm Erica Voss. I also work at Johnson & Johnson. Early in my career at J&J, I focused on developing CDMs. I have a background in working with large data sets. But now my current role at Johnson & Johnson is to help make sure that we are addressing clinical questions, safety questions that the business has. So today, I'm going to help open the talk, and then I'll help close out the talk at the end of the day. Okay, a little housekeeping. So hopefully you have registered. If you do not have a badge, at some point this morning you need to go and get your badge. It really just helps us know who showed up and who actually was able to attend the event. We encourage questions throughout this presentation, and there's two ways to do that. First, we have one mic, so we will pass the mic around. Please wave for the mic because it not only helps people in the room to hear you speaking, but we are also recording today's session. So when people see this in the future, they'll want to hear your question as well. But we also know sometimes people are a little shy, and we have an MS Teams meeting invite. The faculty will be monitoring the chat during today's presentation. So if you want to ask maybe a simple question on the chat, feel free, and we'll be monitoring that. If you didn't get today's meeting invite, just ask somebody sitting next to you. I'm sure somebody can just forward it to you. Like I said, we are recording today's session, so if you want to go back and watch something, you will be able to do that in a not too distant future. Very important, the locations of the restroom. I think you have to just go out and then to the right, and you'll be able to do that. And I think the OHDSI, or the network name, is on the table, so if you do want to connect to the internet here, you can do so. Okay, so for today's agenda, we'll go through a quick introduction, and then after I'm done, I'm going to turn it over to Mui, who's going to talk about the data standards. Once Mui gets done telling us how to convert our data into a standard format, we're going to turn it over to Lin Ying, who's going to talk about our standardized methods. So specifically, in OHDSI, we think about characterization, population level estimation, and patient level prediction. After that, we'll take a short break. You guys have already probably seen the coffee and stuff that's outside that should be available. And we get back from the break, we'll go into open source analytic tools where Jenna will walk us through, like, once we have standardized data and we have standardized methods, how do we actually apply that using our tools? Then Danny will talk us through, okay, now that we have tools and we're able to run an analysis and we get data, how do we actually interpret that data and think about that? And once we're done with that, I'll come back and I'll talk a little bit about, if any of this interests you, how you could actually become part of the community, and what opportunities are available for that. And then we should have some time for questions and answers. So I'm going to get us started with a little bit of introduction into OHDSI. So what is OHDSI? OHDSI is the Observational Health Data Sciences and Informatics. It was founded in 2014, and the Central Coordinating Center is not far from here. It's in Columbia University in New York City. And OHDSI is a multi-stakeholder, interdisciplinary, open science collaborative to bring out the value of health data through large-scale analytics. And I'd like to stress the multi-stakeholder. Really, the work that we want to do within OHDSI takes a lot of different talents. So if you even just look at the faculty, you have people who are experts in data, you have people experts in methods, you have people who are experts on the clinical side. So it's okay if only parts of today's presentation resonate with you. You don't need to be an expert in all of these things, because we come together to bring that expertise. And it's interdisciplinary. We need all different types of people. We want patients, we want academics, we want the private sector, we want the public sector. People have to come together in order to make this all work. So OHDSI's mission is to improve health by empowering a community to collaboratively generate the evidence that promotes better health decisions. So we want to improve health, and our vision is a world in which observational research produces a comprehensive understanding of health and disease. So our mission is to improve health, and we want to enable that by using observational data. I like to touch on OHDSI's values because I think it's core to the community. So OHDSI values innovation. I think this is important because just because we've done something for 50 years doesn't mean we need to continue doing it that way. So OHDSI likes to challenge the status quo even within our own community. So even if we've done something for 5 or 10 years within OHDSI, it doesn't mean we can't do it better. OHDSI also values reproducibility. I think a common criticism in the field of observational research is that you take one researcher over here on one data set, and then you have another researcher over here on another data set. They ask the same question, they get different answers. And so OHDSI really wants to crack that nut of saying, how can we produce accurate and reproducible and calibrated results? OHDSI also values community. Everybody is welcome. All different types of people are welcome, and we kind of touched upon that earlier. And in order to bring a community together, we need to value collaboration. So you can't, if you have all these different people, we have to facilitate them working together in order to get all those skills together. OHDSI also values openness. So we want everything that we do within the community, we want to make sure that it's open and available for other people to see and question and provide feedback to. We really don't want to have a black box approach to how we are doing patient safety or improving the healthcare as well. And OHDSI values beneficence, and I take this to mean is that if you are part of the community, within the community we try to do right by each other, and so that you need to keep that in the back of the mind as you're doing projects and you're collaborating with each other. The OHDSI community is international, and so you can see here little dots of all the different places where we have collaborators. Currently, there are over 4,000 collaborators in 83 countries, in 21 time zones, which sometimes can make it a little difficult to collaborate, over 6 continents, but we're all one community. Now, over the course of the day, you're probably going to hear the word OMOP, and so I always like to tease this up because it's part of OHDSI's history. OMOP is the Observational Medical Outcomes Partnership, and in the US, this was a public-private partnership that was established to think about how can we use healthcare data to inform the effects of medical products. So this was a 5-year project, and it thought about developing methods. And I would say one of the most important things that came out of that 5-year project was the development of the OMOP Common Data Model. But because it was only bound by 5 years, after that we needed to think about, well, how do we continue this work? And through doing the work, a lot of people came together and were passionate about what we're doing and saw a value. And so after OMOP, that's when OHDSI was born. Okay, so that's like a whirlwind tour of OHDSI. And I'm going to pivot a little bit now to talk about the example study. So for those of people who were able to read this study, I'm going to just talk about it at a very high level. So this is the large-scale evidence generation and evaluation across a network of databases. That long string of text stands for legend, and you're going to hear that word over and over today as well as tomorrow. And this specific legend study was assessing validity using hypertension as a case study. So we refer to this one as the hypertension legend study. Now tomorrow during the plenary, you're also going to hear about a legend study, but that legend study is on type 2 diabetes. So legend is really a framework of how we think about addressing clinical questions. And so this is just the hypertension one, and tomorrow is a type 2 diabetes one. Now, when I like to explain legend to people, I actually think this quote from Patrick Ryan perfectly sums up what legend is, as well as what the paper that you read is. And so I'll read this. Patrick says, rather than inefficiently conducting bespoke analysis, one question, one method, one database at a time, leaving us vulnerable to various threats of scientific validity, Legend provides a systematic framework that can reproducibly generate evidence by applying advanced analytics across a network of disparate databases for a wide range of exposures and outcomes. And I know that's a mouthful, but I really think in one sentence he encapsulates that paper and what Legend is. But in order to kick us off, I'm going to talk a little bit about the components of Legend that are going to play, or this specific study that are going to play a role throughout today's lecture. So I like to think of every study that we do as kind of having building blocks that come together to form the final product. So one building block that you would have within this study is the actual data. So in this study, there were 9 databases. We had claims databases as well as electronic health records. And the only way that we're able to use 9 databases in one study is if they're standardized. And so Mui is going to talk through how one would actually go about standardizing data. Now, another building block that's important to performing studies is phenotypes, and phenotypes are essentially algorithms that we use and apply on data to find people who have specific characteristics. So, for example, in this study, there are 58 treatment phenotypes. So these are phenotypes like lisinopril. They're considered treatments for hypertension. We also had 55 health outcomes of interest. So for example, in this study, there's cardiac arrhythmia. That's when you have an irregular heart rhythm for one reason or another. And so we've in order to perform the study, we created phenotypes in order to find patients that exhibited those characteristics. Now, today, we aren't going to talk through the science of developing phenotypes. There are going to be workshops and probably discussion tomorrow that will talk a little bit more about that, but it's an important building block, and you'll hear about it during today's presentation. Next, another building block that's important to performing a study is what's the study design. And one thing that we'll do in OHDSI is we kind of have a standardized way of how we even ask the question. So because this is an estimation question, we typically ask these questions like this. Does exposure to a drug, in this case let's take lisinopril, have a different risk of experiencing some type of outcome, let's say cardiac arrhythmia, within a specific time horizon relative to another drug, let's say amlodipine? And so we even have a standardized way of just thinking about the actual question. Now, if you ask your question, you're going to need methods to actually implement that question on the data. And so within OHDSI, we have things like how we perform propensity score models, as well as empirical calibration. So both the study design and methods, Lin Ying is going to talk a little bit more about today. Now, if you have your methods and you have standardized data, you need tools that can actually implement those methods on the standardized data. So Jenna is going to talk about Atlas and Hades and about using R packages to implement those. And once you have all your building blocks, you're in a position where you can generate clinical evidence. And Danny is going to talk through the interpretation of that clinical evidence. So with that, I am going to turn it over to Mui, who's going to talk through data standards.
Oh, I got to take these glasses off. Good morning. Oh, this is too tall. Erica, you got to learn to move this down. You're like this tall. I'm like this short. Morning. Everybody have a good morning? You're awake? Ah, this crowd sounds so boring. I'm the one who had 2.5 hours of sleep last night. Come on, people. Yeah, make some noise. Say good morning. Not for me, for her, right? You got to clap for her, for Erica. She went through all that and, okay. All right. Thank you. So like Erica says, my name is Mui Van Zandt. I'm going to spend some time with you guys talking about the Open Community Data Standards. All right. Before we go into, open community data standards, I just wanted to set the background to talk really about real-world data, right? When you talk about data standards, you have to talk about real-world data and where real-world data comes from and how the fact that it's actually not that perfect and it comes from has many different challenges, right? You can see here we get data from patients, we get data from pharmacy, we get data from claims, we get data from everywhere. And I do have to put the disclaimer that I stole this from IQVIA, okay? So I do have to put that there, that I stole this slide from IQVIA. So, but the thing why we go and get real world data is because it can bring us a lot of insights, right? We can get cohort definitions. We can get more understanding around the patient, the prevalence, the safety, the surveillance, and comparative effectiveness, right? But like I said, there's a lot of challenges, though, to real-world data. And one of the challenges that we have is the fact that all these different data, dispersed data from hospitals, from claims, from PROs, I should say patient-reported outcome. Don't ever use acronyms in a class because I don't know if people ever know what those acronyms stand for, right? So with that, we have it from all over the place. And one of the things that you probably do today is every data asset you actually have to sit there when you want to do analysis, understand the database, understand its structure, and then write the code. And if you want to do this on another database using the same analysis, you have to do the same thing. So you're writing the code twice, right? And most of the people who write those are either SAS or Python experts. Right? They write it, and they're all spaghetti code, and that's why it looks like that little, right there, all that's cable cords right there, okay? We are computer geeks around here. It's kind of like your laptops right now, right? You're all plugged in. I see some folks with big converters. Oh, those are iPad chargers. But I'm sure some of you guys are from international who brought an international converter here just so you can plug it in, okay? That's the problem that we have with data as well, because it comes from all these different dispersed systems different countries. You don't understand half of what they say sometimes because people key it in all they want, or you come from clinical notes, right? So that's why we want to standardize. We want to be able to standardize all that data so that then when we do the analysis, it's only the same, it's the same analysis over and over again, right? So then there's that trust of the analysis. Do you trust the ETL? I don't know, but at least you can trust the analysis, okay? And so like I said, once you can have your data in one model, this is how it works, right? Your data is in the same model, and then you can actually take those standard analysis that we have in the OHDSI community and be able to run that against your data, and with that data never leaving your environment, okay? Your data stays where it is. No one takes it. I'm not going to take your data. She's not going to take your data. No one's going to take your data. We send the queries and the analysis in. You run it, you check it, you double check it all you want because we won't put a virus on it, maybe, okay? And then you just send us back the aggregated results. That helps us avoid a lot of complications, right? Like hospital data, PHI, right? Or you have legal saying you can't share your data, okay? Very private stuff. Well, you're only sharing a count. You're only sharing how many females, how many males has X, Y, and Z. Or you're sharing, these models that the other folks are going to talk about later, okay? So that's what you share. And then at that point in time, we can do analysis against that, okay? That's the whole power of the OMOP CDM, which leads me into the OMOP CDM. What is the OMOP CDM? So Erica said OMOP stands for Observational Medical Outcome Partnership. I learned that if I say somebody's name, then they look up. Okay, like if I say Danny's name, Danny looks up because they're all staring at their computers too. Okay, just like me when she said my name, I'm like, what? She called me, what? What? So when we pay attention, that's the other reason why we ask you guys to put your name tags, even though I can't see them, is so that we can call you guys out. Okay, but I do know a few people in this room, like Sergio right there, saying he's going to look up. See, he looked up. Okay, so back to the OMOP Common Data Model. Sorry, I have to keep you guys awake somehow. Right? Am I doing well so far? Okay, I see nodding. Okay. How about the ones in the back? Am I keeping you guys awake? I can't see you. I have to put my glasses on. All right, good. Okay, so the OMOP Common Data Model, okay? We're currently on 5.4. Some of you guys might be on 4.0. I hope not. Okay? But I have heard of that before. Some of you guys might be on 5.0, which is okay, but you should probably upgrade all the way to 5.4. It's not too complicated. Okay, but in the OMOP CDM, what we do map is we take your data and we map it to who, where, what, when, how, and why. Okay, so if we look at the key domains, this is what the OMOP CDM looks like. It's no different than any other database. Okay, we just happen to use the OMOP CDM. And so you can see here, you have people, right? And then you have everything about the people. You got your standard health data systems, you got your derived data system, derived stuff, your standard, and then the vocabulary, okay? So then we're gonna talk a little bit about where, the what, and the who, the where, and the why, the 5 W's and the H, okay? So if we go into the who and the where, right, we're talking about the standardized health system data. So this is the location, which is the where, the care site, which is the who, and then the provider, which is the who, okay? And then, of course, that ties back to the person. We call people person, we don't call people patients because we feel everybody's going to get sick, and patient just makes me sound like I'm a sickly person, okay? So we like person more. We like to be upbeat about our research, okay? And then when you talk about the what and the when, again, it's we have to then go into like drug errors and how long things have been, right? How long things have taken, as well as the healthcare systems, and then also the what and the when has everything else with all your transactional data, like what procedure was it, what drug did you take, when did you take those drugs, right? You had a lab test. When did you get the lab test? What was the results of those lab tests? So all the transactional tables are what we call the what and the where. When, because that's stored in there, right? And then the how is also becomes then the vocabulary. Like, how did I do this? Was it a certain procedure that I took, or was it through an injection versus a oral medication, right? So does, uh-oh, my little animation doesn't work so well. Okay. So at a high level, right, that's the CDM table. Now, how many people actually know the CDM? I should have asked that first before I went through all that. See? So I didn't have to go through. Was that very clear to you guys what the CDM is? For those that don't know it, those that know it, put your hands down, man. You already know it. All right, so I wasn't clear on what it is for those who don't know it. Is there any questions as to why I didn't explain that well enough? It's such a shy group. Okay, I'll go into a little bit about our OMOP CDM principles. Okay, so as you can see earlier, we had this OMOP model, right? It had the person, had a bunch of transaction table, had a bunch of provider location table, healthcare table, and then vocabulary tables, right? So one of the things we are very, this model does is it's very person-centric, okay? Very patient-centric. Everything is against the patient. You have the person, and then everything else has a person ID attached to it because everything is, hey, what happened to the patient? We're not provider, we're not provider, or we're not payer specific, right? So we're very person-centric. Now, one of the main things that we'll spend a lot more time on in a bit is around the vocabulary, okay? The main difference between the OMOP CDM and some of the other ones that you hear of, FHIR, CDISC, I2B2, all those, main difference is that vocabulary, okay? Because we don't only standardize your tables, but we actually standardize all the medical ontology that is around as well. So we put everything we harmonize everything into one medical coding system. Okay, well, not one, but a few medical coding systems, okay? So, because it's no different. Again, you can standardize your table, but then like with FHIR, when you're doing that, right, it has its own XML and its own fun stuff. But if you go to the medical coding, it's whatever the heck you put in. And Hospital A likes to name things their own way. Even though there might be national standards, they still want to put in things their own way because we got to have our own specific hospital codes, okay? And then if you do analysis with somebody else, Hospital B, who has their own unique codes as well, you're still having to go through this, hey, is this code right? Is this analysis right? Because your code list and my code list might not match. And what you think is diabetes, I may not think is diabetes, right? So that's why it's very important not only to standardize the structure, but also to standardize what we call the vocabulary, okay? Which is your ontology or your medical coding system, okay? And then we're very, very, very domain-centric, okay? So OHDSI stands for Observational Health Data Science and Informatics, right? It's all around research, okay? So OMOP and OHDSI was created for research purposes. Now, it is being expanded to other things, like you might have one of the tags on that says Clinical Trial Working Group, but we're going to ignore them for now, okay? But it's made for research. So we're very research specific. So thus what we base our standard on is what actually happened to the patient. Not where it got medically, not who claimed what, not who paid for what health insurance, right? It's all about what happened to the patient. So we have domains. We have drug domains. We have procedure domains. We have condition domains, right? What you're going to find out if you're doing data conversion with your data are things that you think are ICD codes. To us, may be observations. Or to us, what you think are procedures aren't just procedures. They're also drugs, right? So now, for the record, caveat, I am not a medical person, okay? I'm a computer geek. So the only few examples that I know are things like injections, right? In the United States, we key them in typically as HCPCS codes or CPT codes, okay? But what's happening to you is that's the procedure. So the hospitals are keying that in so that they can get billed for that procedure, right? But what's happening to the patient is a drug is being injected, okay? So when you convert that over, you're going to convert that over into two records. One is the procedure itself, but the other is actually the drug. So in our case, you actually will have two different transactions in two different tables to the one that you had in the original in your original source data. Okay, that's what we mean by domain oriented and also patient centric. We do accommodate as much as we can for as many different various sources where possible, right? Claims, PROs, surveys, EHRs, registries. And if you don't like any of those, or if there are ones that you don't, that doesn't match, then you work with the OMOP CDM working group. And they will be glad to accept your proposals. You have to go through a process and get all that incorporated, right? And then we do preserve your original data prevalence and also the data sources. So a lot of people say, hey, when you move things to OMOP CDM, I don't know what happened to my data. Well, it's still there, okay? Your source codes are still there. You can still run things using their source code. Don't quote me on that, although I'm recorded. So, but you can do that, okay? So it's still there. You don't lose anything. There are some things that may end up dropping, but that's because you use certain fields to create the business rules for what moves into the OMOP CDM, right? So then, of course, some of those we may or may not bring over. But you can actually write rules to figure out whether or not you can preserve those, okay? Like I said, we are extendable and evolving. There is an OMOP CDM working group. There's a vocabulary working group. If there are things that we aren't capturing, then work with those working groups and we can look at incorporating them, right? We keep going up in versions. Right now it's at 5.4. There's always talks about, well, there was a version 6, but we downgraded it again. But there are talks, about next versions all the time, okay? And we are database platform independent. We're also technology independent, okay? You can do your conversions in R. Some people do these in R. Some people do these in SQL. You can do them in Python, C, whatever you want to do. Okay, we are platform independent. Now, like I mentioned, there is a CDM working group. Okay, so for those who really wants to learn more about the CDM itself, there are previous tutorials. There's Eden, and then there's the book. Okay, how many of you here know about the book? Book of Odyssey. Wow, everybody's done their homework. Cool. So we have lots of stuff. And then with the CDM model itself, the wiki site, was it last year or the year before? We spent a year redesigning the whole website, updating a ton of the rules, okay? So there's a lot of work that goes in there. All that documentation is on GitHub. There's the Book of Odyssey, there's the CDM. And then if you need anything like the working group, or if you have any questions, Claire's name is here. Claire, don't ask me, ask Claire. Okay, her name's right there. Okay. What this is telling us about, which is gonna help me segue into the next section, is that we spend a lot of time on our vocabularies. Okay, that ontology mapping, we don't just spend our time on the CDM because we feel the vocabulary is just as important as the CDM itself. Right? So we spend tons and tons of time on that, and we've translated a lot of those codes over. So a lot of the ICD codes that you have, they all are mapped to SNOMED already, okay? Your drug codes, most of those are mapped. We've done a lot of those in many of the different countries, both in Europe and in Asia-Pac. All right, the rest of my session, because vocabulary is that important, is really going to be around the vocabulary. Erica's gonna time check me, right? Okay, good. So I don't talk too much. Okay. Yes. You're not allowed any questions.
Have you translated Canadian drug identification numbers?
We've translated drug codes, Canadian drug codes. I think they're DPD, your national drug codes. Yeah, they've been translated into OMOP. So we'll show you in a bit when we go into Athena, right? I think we did that 5 years ago. So. Yes, we have. Thank you for that question. Okay, like I said, we're going to go into this. Source codes, concepts, and mapping. So the first thing I want to talk to you guys about is the source codes, right? So source codes can be, so we have things called source codes and standard codes. Trying to get the terminology. Source codes are those that comes from your system, your current system. Okay, they could be from international terminology or coding systems. They can be country specific, right? They can be freeform text fields, and they can be maybe EHR systems instead. Like I said, Hospital A likes to create their own coding system. Okay, so that's how source codes work, and we have different types of what we call concept codes. Okay, so each terminology is considered a concept code. Okay, so we have non-standard ones, And those are your source codes. Okay, all your source codes are what we consider, well, maybe if you're using SNOMED, then you're standard. But we have those terminology and those ontology that we call non-standard. Okay, and what you have to do is map them to the standard ones. So if you're using ICD 9, ICD 10, ICD 11, those are considered non-standard. Okay, you have to map them to SNOMED. Okay, and then we have classification codes. Okay, those are the higher level ones like the MEDRAs and the ATCs. Okay, which then you can get that hierarchy, and I'll show you in a bit how that works, the hierarchy across all of these. Okay, so some concepts to remember. Okay, and like I said, you have to take the non-standard ones when you're doing your conversion, map them to the standard ones. It's the only way you're going to be able to run the same analysis as everybody else. Okay? So let's talk a little bit about how you do that, how you do this source to concept mapping. Okay? So you have these source codes, and as Erica was talking about, see, she looked up. We are using the hypertension, right? The hypertension as the paper that you guys have read. So these codes are coming from, it came from the cohort definition list that we had, right? So how do you find these source codes in Athena, and how do you then map them over to the OMOP CDM, right? So you have to take the source code, and then if you're doing a SQL, you basically have to go find them using the SQL statement, or you can use what we call a tool called Athena, okay? So if we go to Athena, here, this guy, yes. So Athena, you can do, it's athena.odyssey.org, okay? So you can do that right now yourself, right? When you first log in, you have to hit this little accept button. It's just saying, because SNOMED requires a license, that you are agreeing to that, okay? So that you can search this. So some countries, SNOMED isn't available because the country doesn't have the license. But Odyssey actually has a research license with SNOMED, so that's why this has popped up so that we can track it. And what you can do is actually just put in here what you're looking for, right? So in our case, we're looking for this pre-existing, ooh, thank goodness for this, code here. So what you just do here is you type it in here, and then it'll search for it, okay? Now you can see there, you can filter on the side. Here's all the different domains, the countries, not the countries, the conditions, the devices, the gender. You can do it by a vocabulary. So vocabulary are the different type of coding systems, right? You got ICDs, you got whatever you're looking for. So in our case, you know, it's probably an ICD code, is my guess. I don't know what I picked. I forget what I picked. Okay. And this here is the code. That's your source code, right? This is the concept ID. This is the OMOP ID that goes with your source code, okay? In our case, we always have a concept ID. It's a unique ID to the OMOP vocabulary itself only. Why do we do this? Because this particular code itself can be repeated across multiple ontology systems, right? So thus, it has to be very unique in the OMOP system. Now, in the OMOP system, this code is unique. This ID is always unique. Even if one has been nullified, we don't reuse codes. We don't reuse IDs. I'm not NDC, okay? I don't reuse them. So that one ID is always that one ID. If we made a mistake, we'll invalidate this one and create a new one. We won't just update it, okay? So you can do this, and then what you can do is, like, for example, in this particular case, I have to go, it's an ICD-10-CM, but then I have to say, okay, what does this map to? Because this is non-standard. You can see here it says non-standard, right? So then you have to click on this, and you'll see down here it says non-standard to standard mapping. You can see it actually maps to two different things, not just one, but two different things. Okay, so that's something you will see in the OMOP vocabulary as well. Okay, sometimes it's a one-to-one mapping, sometimes it could be a one-to-multiple mapping. Because in ICD codes, you can see here it's a pre-existing type 2 diabetes, but also in pregnancy, right? So they're mixing two things. So that's why it's a finding related to pregnancy is one of the codes that it maps to, and then it also ties to the pre-existing type 2 in pregnancy, okay? So you will find this where you can ultimately get more than one record. Any questions so far? We have a hand way back there. Who has the mic? Exercise for somebody, not me.
Where was the hand? Oh, thank you.
You have to tell us who you are, where you're from, how long it took you to get here. No, just joking. Just joking.
Hi, I'm Navi. I'm from Genentech. My question is, if we want to eventually find out this code, this which is ICD code, and patients with this code specifically, do you have to then use AND condition if you are using SNOMED code?
So if you're looking for this specific code right here, and only that specific code in the OMOP CDM, there's in the condition table, there's a source value column, source concept ID column. You could use that to find it, just if you're looking for this particular code. Okay. Does that make sense?
Yeah.
Yeah.
Thank you.
I have another question way over. Oh, no, over there first, so that she doesn't have to walk so far.
Yes, thank you, Mui. I have kind of a higher level question.
Yeah.
So sometimes in database analyses, we have validated algorithms to identify certain phenotypes. So how do we think about implementing those when we're harmonizing, different codes across different databases?
Now you went into analysis and phenotypes.
I'm sorry.
Okay. Those are the three other folks on the table. Can you guys take that one? Can you ask the question again?
So the question is, if you have already a validated algorithm for finding patients, let's say it's an ICD-10 validated, that's how you're going to go out and find patients. And maybe there's some inclusion, exclusion rules. So there is a whole science that we believe in terms of phenotyping. And so if you have an algorithm, we can actually use a tool called Atlas, and then we can actually put those inclusion, exclusion criteria into the tool. And then we actually have tools to then evaluate how well that phenotype is performing within the data. So, it could say hey, given the definition, we might recommend additional concept IDs that you might not have considered. But that's a whole conversation that we're not going to get too much into today, but there are lots of people who think a lot about phenotyping within the community. Sort of answer.
Before you go, she was first over here. So Erica, I'm making you walk all the way over there. Or were you going to help answer that question?
Oh, Jamie, Jamie, wait.
Wait, Jamie. Well, come on. We have an extra teacher in here.
Once you've taken that validated algorithm from whichever source and translate it into an OMOP compliant algorithm, it then becomes fully transportable to any other data set that's been transformed to the OMOP CDM. So if you've validated it in one, you can then build it in any CDM and then check its performance characteristics to see if they're consistent across sources.
Hi, my name is Anya. My question is about licensing. You mentioned it briefly. I don't know if you could explain a little bit how it works. So SNOMED is one example. There might be other vocabularies that require licensing. So does that mean that when we're converting to OMOP CDM, we need to take care of licensing beforehand so how does it work?
So many of the standard codes has their own, it's free. Right, so most of them are free. RX norm is free. SNOMED does require a license. Procedures, LOINCs are free, right? So for those, when you're converting them over, you don't have to take much into account. SNOMED was the biggest challenge we had, and like I said, with SNOMED, the OHDSI leaders had a discussion with the SNOMED international community, and basically, if you're working within the OHDSI environment and in the OMOP environment, then you can actually use that license for free. You can actually use Athena to download the vocabularies here. And when you hit the download button, it will ask you, for those that do require a license, if you already have a license. So we don't in Odyssey do not manage anybody's licenses, okay? You don't go buying FDB or GPI through us, okay? We don't do that, okay? But what we'll ask you is, can you show us proof that you have the license, and then we'll open that up to allow you to download it, if that makes sense, right? For the SNOMED one, we just need you to log in, because then we register that, and then we send it back to the SNOMED. Okay? All righty, back to this deck. So again, that's how you go and look up all of these different codes, right? So again, you can use athena.org to look up everything, and then it'll find the ones that you're specifically looking for. I won't go into all these different scenarios, but the other way you can look this up, not just the codes themselves, but you can see here the different like the unit or the route or the gender, right? It's not just your ontology. It's not just your coding system. Erica, I got another question over there. So, hey, I get questions.
So these are, the examples you have here for free text are very clear and obvious. What do we do about things that are, like me as a human reading, I can see that F means female, cm probably means centimeter, all the variations there. Mm-hmm. Like, where do you draw the line on creative interpretations?
Well, these are actual, they will actually map to what we call standard vocabularies, right? So we actually have in here, if I get rid of all these different domains here that already exist, like gender. So what you would have to do is match it to one of these named descriptions that already exist here.
So exact string matches?
Yes, yeah. So that's it's vocabulary, right? Okay. Yeah. You can use NLP. Chris, yes. I got another teaching assistant here.
Sometimes these are conveniences for sure, that the vocabulary will come with a bunch of, think of it as published. As you see, each of these strings here have like a vocabulary that they might have came from. You can see like Nebraska and whatever, but you might have, like you said, like you do in your own data source, F and M, right? That's just for your thing. So in the process of your ETL, you can defer mapping from what we already provide in a vocabulary to help you go from these custom codes to the standard codes. But you could also provide your own set, and this is just an ETL exercise. If you know F and M mean male, female, then go ahead and implement your own additional mapping checks. So you could say, go to the standard vocabulary to map, and then if I can't find it there, try to come to a custom map that you've already curated yourself. And if you fail all that, then there's basically an unknown type of value that you can put into your data.
There is an ETL class, I believe, in the afternoon, which they'll go into a lot more details there. Yeah. But what we ask, like Chris said, you know what you have in your database, you just have to know how it maps to the OMOP CDM, right? Because what we want you storing in the OMOP CDM when it comes to like the gender ID, concept ID, it should be this 8532 if it's female and 8507 if it's male. Because that's when people run the analysis and the way Atlas is built and all the tools that's built, that's what they're looking for, right? Because everybody else is converting it over to here. Your source code could say 1 or 2 or, you know, A or B. Right, but you know through the ETL business rule, A means female, B means male. So then you map it to these guys, right? Now your own source code, you can have a concept ID as well, but you would then create your own table of those, if that makes sense. So, okay. Thanks for all the questions. All righty. Okay. The other scenario that we just talked about, thank you for leading me to that, is if those codes don't exist in our standard vocabulary, okay, you can actually ask Odyssey to incorporate that, right? So someone just asked earlier, right, do we have Canadian drugs in there? Yes. And again, it's through this whole process. There's a whole document of how you can add it to the vocabulary Athena process. Or the other thing, if you don't want to bother with it because it's just your type of codes, then you can create what we call 2 billion series. Okay, because we don't think we're going to end up with more than 2 billion, non-standard standard codes, so you can create your own 2 billion series. But that requires a lot of maintenance work, because you have to make sure that you're not interfering with the normal vocabulary, right? The ones that you download and your own custom one. Okay, so there's multiple ways to doing this, but you can actually see quite a few. It's in the when you go to the ETL class, they'll talk about it a lot more there. Okay. So I talked about earlier, the different coding systems. You got the standard ones, you got the non-standard ones, and then you got the classification ones, right? For a majority of the standard, I shouldn't say standard, the known ontology coding systems, we have a hierarchy already built into the OMOP CDM, the standard vocabulary tables, okay? What that hierarchy allows you to do is actually go up and down the whole chain. Right. So in this case, for example, atrial fibrillation, if that's the code that you're looking for, it will tell you, if you use the hierarchy relationship tables, what its descendants are, so its children, as well as what its parents are. Okay. So again, it was SNOMED. The one reason why we picked SNOMED is you can have multiple parents. Right? ICDs, you have one parent. Here you can have multiple parents. Atrial fibrillation, one of its parents is fibrillation, and then the other is atrial arrhythmia. That took me forever to learn how to say. Okay. I'm telling you. Atrial fibrillation. And then I'm told, you just need to say AFib. Why? Why not just give me AFib to begin with? Okay, but it can all, like I said, it can keep going up, right? And you can keep going up, and you can keep going down. So that's the power of what we have in OMOP. Now, where do we get these? We didn't create these ourselves. We just took them from the standards that are already there. We brought it in, and we put it into a relationship table where then you can do all this searching. Okay, so just for clarification, right? Odyssey didn't go and create all these hierarchies ourselves. Okay, they already exist in the SOMAT system. We just brought it in and made it more convenient for our folks to be able to look into. Okay, so I'll skip all these. So you can see here, like I said, you can this is what we call an ancestor. This is what we call a descendant, right? So up here, the higher level one, just like your family tree, your ancestor versus your kids. Right, your descendants. So same concept here. And then we have levels of separation. So from atrial fibrillation to disease of cardiovascular system, that's 5 levels of separation. Right, so this is one level of separation. These are my parents, my grandparents, my great-grandparents. So level of separation is what we call these. Okay, so in this case, if I go to supraventricular arrhythmia, it's 2 levels of separation. Okay, and the same thing exists. So here's I'm going to talk a bit about our standard conditions, right? So this, like I said, standard conditions, we use SNOMED codes. The classification that you can actually link it to is METRA, which is typically used in clinical trials, right? So you can actually do this linking where that hierarchy, you can actually map from the SNOMED hierarchy all the way to the METRA hierarchy as well, okay? And then the source codes, that's everything else underneath here, that then maps to the CDM codes, okay, the SNOMED codes. So there's this whole hierarchy you can do, right? These are what we call standard concepts. These are what we call classification concepts. And these are what we call source concepts, okay? If you want to do it, you could do it this way, which is a SQL statement, which you can type. This works really well. Or you can use the tool like Athena, okay? So if you end up using a tool like Athena, you can type in, get rid of that, right? Atrial fib. And you just have to find the standard one. So this one right here, I know because it says standard. Maybe it'll spin, maybe it'll do something. There it goes. And then what you can do is there's a hierarchy tab right here, okay? I need that Jeopardy, sound. Ding, 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 It'll show up eventually. Right, so here you can see atrial and these are its children, there's its parents, and it keeps going up and up and up and up and up. So you could use this to look at it if you're looking for one, okay? If you want to look for a bunch of them, it's better to write the SQL code or to use the SQL code, right? Or Atlas, which some folks will talk about later, okay? This is the drug hierarchy, similar concept, right? We have standard concepts here, which is RX norm. This is a little bit outdated because we now have CVX in here as well for injections, right? But then you have drug classes up here, which are your drug classifications. And then you have your source codes that are down here, okay? That helps us look at this. And then we also have procedure codes in here as well. Again, like I said earlier, because of things like injections, right? There's still drugs as well. Okay, this is the procedure ones. There's really no, there's some standards, but we're still working on trying to standardize everything. Okay, so some of these are HCPCS codes, CPT codes, SNOMED codes, ICD-9 procedure codes, but they map from your source codes. Okay, same concept. Now measurement, the hierarchy there is actually with the newer version quite interesting because we have both LOINC and SNOMED as codes, okay? So what you'll see here is one that has a joint hierarchy between the SNOMED and the LOINC code, okay? Which is glucose measurement, and then you have these glucose measurements, but then there's a more granular one that's a LOINC code. So if your data is at this level, it will actually help you map up to the SNOMED hierarchy, okay? But then we have those that aren't joint at all, that they are their own unique codes, right? This is the SNOMED one versus this is the LOINC one. So it depends in your measurement. Sometimes they can be mixed. Sometimes they are on their own, okay? Any questions? I went through that pretty quickly. Again, there's an ETL class later this afternoon. And then also you got the wikis, you got the tutorials where we actually do, there's an 8-hour class. If I think you put it on 2 times speed, you can get through it in like 2 hours. That goes into a lot more detail about this if you go to the odyssey.org website. Okay, I have a question over there. And we don't want you to be loud because it's being recorded. We need every evidence that this class was attended by humans.
Yeah. Is there, so as you're kind of mapping your own data to the CDM, is there any sort of like central quality assurance body that does review mappings and kind of make sure that it is meeting the standards of like the Odyssey community?
There's a whole data quality working group to do all that. There are, right? We have the data quality dashboard, one that helps you look at the data that you converted over from the OMOP CDM into the OMOP, or from your source data into your standard data. That checks some of your vocabulary, but it doesn't check all of your vocabulary, right? The one thing we do check for, which a lot of people make mistakes on, is they put non-standard codes into the standard concept ID field. Right, because that whole mapping thing, the whole mapping is very confusing, right? So we have checks like that. But the other way that gets checked is actually when you do try to run your analysis, right? Like Jamie and others were talking about earlier. See, he looked up. You just gotta call their names out and they all look up, okay? You have things like the cohort diagnostics. You have tools like that that helps you look at codes to see if you might be missing stuff. Right? So there are ways to check it, but it's not that we check everything, right? As you probably know, it's next to impossible to do all that. But yes, there's a data quality dashboard as well as the quality working group that's trying to improve more and more of the data quality checks. So Claire runs that as well. You saw her name earlier in the deck, so you can contact her as well. Or just go to the Odyssey journey and join that working group. So any other questions? Yes. You're just trying to make it so that I go over.
I am Michel or Michael, like you know, Walravens or Walravens, okay, from Belgium. I am involved in this stuff because I started up some initiative to translate the OMOP book. Maybe you know, I don't know. But my question is about SNOMED, the relation between SNOMED and OMOP, because I rolled into Odyssey via SNOMED. Okay, where I also did a lot of translation work. First of all, may I suggest never to confuse the names translation and mapping. Can be dangerous. Okay, but my question is next. If I got you right, when you map a SNOMED term into OMOP, you respect the ontology of SNOMED.
Yes.
That's right. Does that mean that, in fact, OMOP is taking over the SNOMED ontology?
No.
Okay. But then when you map, for instance, an ICD-10 term or word into OMOP, then I see that you go over SNOMED.
We go to SNOMED.
And you map it to SNOMED?
We map it to SNOMED.
And then you map that ICD-10 term exactly the same as the SNOMED term with which you mapped it.
So when you map SNOMED, there's no mapping of SNOMED. SNOMED is SNOMED, right?
Yeah.
If your source code is SNOMED, then that's the code, that's the standard ontology.
I understand that,
Okay.
yeah.
But if you have an ICD code, then we map it to SNOMED.
Okay, but that means that you put it in an ontology, and that's very important for your OMOP system also.
We put it into
But
the CDM, yes.
How do you handle? What do you do with terms in ICD-10 that are not exactly mapping with SNOMED terms, but who are near SNOMED terms?
So mapping is not always 100% correct, right? So what we do, and there's a whole vocabulary team that does this, right? When they do the mapping, they map to the closest one or the higher level one, right? Because sometimes ICD codes are very unique. Like when we do, and we did this in China, right? ICD-10-CN is actually 7 digits. It's not 5 digits. They actually can go all the way down to 7 digits. So it's very, very granular, right? So when it's that granular, because SNOMED doesn't go that granular, we map it to the next highest level that we can find.
Okay, but isn't that difficult, not to say dangerous, for the ontologic structure? Because if you have a near mapping, say, then the parents and the descendants of that near mapping may be not correct.
So again, it depends on your study that you're looking at. Okay, like I said, I'm not a study person. Okay, so I need the study folks to help me in this area, right? But at least with my experience of a lot of the research that I do, right, you don't always need to go down to that granular level. Okay, you typically do research at a much higher level. Okay. When you do want to go down to that granular level, like I said, we still preserve the ICD-9 codes or your source code. So you can still run your analysis on the source code if you want. Okay, you don't always have to run it on the standard code. But again, in a lot of our research, you're looking for, unless you're doing rare disease, right, you're typically not having to go down to that granular of a level. Okay.
Well, I see still some problems, but maybe we can discuss that afterwards.
You can find Christian Reich if he's in this room. If he's not in this room, you can go find him. He can have an argument with you for hours about this. Okay. Okay. We call him the vocabulary god, or Dima. Is Dima in this room? No. Okay. You can find one of those two. Yeah. Okay. They can talk to you about the whole how they map and the hierarchy and which one we pick. I'm telling you, I find assistance.
Thank you very much.
All right. I'm done with my portion. So I'm going to hand it over to our next speaker. Yay, I got hand claps. Look at that.
Thank you, Mui, for kicking off the tutorial with such great passion. It's always a challenge to present after Mui because it's just so hard to match her passion level, but I will try my best. Good morning, everyone. I'm Lin Ying. I'm a faculty at WashU, and today I'll be leading the methods or conducting network research section. So I assume your institution has spent all this time and efforts to standardize your vocabulary, map your concepts to OMOP, and finally you have your data in the OMOP CDM ready to do research, to improve patient care, to answer clinical questions, to do all the great stuff. So let's begin here. And that's what I'm going to talk about. So let's start with the patient journey. Right, this is an illustrative view of a patient journey. All the things that a patient may encounter in their clinical visit, such as conditions, that's diagnosis, drugs, procedures, measurements, vital signs, visit types, so on and so forth. Right, with this data, we can answer a lot of questions. And in OHDSI, we typically group the questions into 3 main areas. For example, someone might be interested in asking a question that's similar to this one: which patients chose which treatments after a specific diagnosis? So questions like this, we call them clinical characterization. We're interested in some descriptive statistics about a population of interest. Or some of you might be interested in knowing more about treatment or treatment effects. For example, you might ask, is one treatment more likely to lead to the outcome than an alternative? So questions in this flavor, we call it population level estimation. We're estimating the effect of some medications or procedures, and we call them treatments in general. Or some folks might be interested in doing more like predictions, patient level prediction, right? We're interested, will an outcome happen to a patient or myself in the near future? So, and we group all those questions into patient level prediction. And I'll walk you through one of them at a time. So let's begin with the simpler one, clinical characterization, right? We're asking basically what is happening or what happened. In a typical characterization study, we need to define the following terms. First is the target cohorts, right? The population of interest. Maybe those are patients that all are diagnosed with a particular disease like type 2 diabetes, hypertension, depression. Then we may be interested in also subgroups. Those are typically we stratify by like demographic factors like age groups, sex, race, or ethnicity groups. Meaning we're not just interested in the population overall, but we might be interested in the differences in men versus women or in racial minorities versus others. Then we need to define features, right? What are you interested about these patients? Are you interested in their coexisting conditions? Or are you interested in what treatments were prescribed to them? Like what concept domains are you interested in them? And you can be interested in multiple domains at the same time. Then we find it's often helpful to also define a time at risk window. Because EHR, electronic health records or claims, or in general, health databases are longitudinal, right? We don't observe someone at a snapshot, but we observe them for a period of time. So what specific time window are you interested about that patient? Maybe interested in pre-treatment phase or post-treatment or pre-diagnosis or post-diagnosis or a combination of those. So defining a time window is always helpful when you define your cohort. So in OHDSI, we typically like to think of cohort as a set of persons who satisfy one or more inclusion criteria for duration of time. And we emphasize that the time component is important when you define your cohort, when you design your inclusion criteria. So I'm going to show you one example study, a characterization study that the OHDSI community did several years ago in 2016, led by Dr. George Ripsack. So in this study, we characterized treatment pathways at scale using the OHDSI network. 11 databases participated from 4 countries, covering more than 250 million patients. And they characterized treatment pathways for 3 studies: type 2 diabetes mellitus, hypertension, and depression. So this is an example figure from that study. This is showing the treatment pathways for hypertension, and we call it sunburst plot. So the way to rate this, okay, I think my mouse moves with it, or it's okay, or I would say. So the inner circle is the first drug that's prescribed to patients with hypertension. So as you can tell, this greenish color corresponds to hydrochlorothiazide. That's the most predominant drug that's first prescribed to patients, followed by lisinopril. That's the orange color. And then if we go out one layer, that is, for patients who start with hydrochlorothiazide, what are the most popular second drug that got added to the patient's treatment plan. So this is how you read this plot. And from this, we can see, we can characterize the full picture of what has happened to patients with hypertension in terms of their treatment pathways. And then I'm gonna, and we did this for diabetes and also depressions, and we do that across many databases. So you can imagine that we'll get sunburst plot, many sunburst plot on, in the paper, and you can check the paper so that we can compare the heterogeneities across databases to see if there's any difference in treatment patterns across countries, across healthcare systems, and also we can compare across diseases. And if I recall correctly, type 2 diabetes is the one that is, the first treatment is always like 80% metformin. So there's a very strong dominant first drug for patients with diabetes. But hypertension, there's maybe 2 dominant ones, and then there's some heterogeneity in treatment practice. However, in depression, like even the first drug, it's evenly split across all the classes. There's a very, not a very strong consensus in what drug we should start treating patients with depression. So that is an example of clinical characterization. This one focuses on treatment pathways, but you can focus on conditions or other concept domains to characterize, to understand better about the population of interest. So I'll pause here, see if there's any questions. It's a quick overview of clinical characterization, but I hope that is the concept or this type of study is somewhat familiar for the audience here. All right, if not, we'll move into patient-level prediction. In patient-level prediction, or PLP, we ask the question, what will happen to me? Or if you're a physician, then you might be interested in asking, what will happen to the patient in front of me? So in a prediction problem, we first define a cohort, the patient of interest. We observe some things about those patients, maybe their diagnosis, medications, vital signs, so on and so forth. And there's a time 0, we call this index time. That can be defined by maybe a treatment initiation or a diagnosis of a specific condition. And then we may ask, in the future, it can be 30 days from now, it can be 6 months from now, it can be a year, 5 years from now, depends on a research question. And we're often interested in whether something will happen. And that something is oftentimes a health outcome. It can be binary, like yes, no, will something happen in the future? Or it can also be time to event outcome, so meaning that we can also do a survival prediction. So let's revisit the hypertension treatment. So let's imagine we come together to study this question. Will a new user of lisinopril experience acute myocardial infarction, or MI, within a year? If I unpack this question a little bit, the cohort, the target population of interest is lisinopril new users. And in the small fonts, those are some of the related concepts or phenotypes we have to define in order to finally identify this target cohort. So the outcomes, acute MI, and the time at risk window is 1 year of treatment initiation. This is how I would unpack this sentence to this question in order to do this study. So let's say we have those ready. Then what we would do is to extract the features about this patient cohort, right? Maybe demographics, medications, conditions from their medical history, and we'll run that through many prediction models, as many as you like, or you can pick your favorite one, and we'll predict whether a patient will have the outcome, acute MI or not. And so that is a very generic prediction question that we may be interested in or may interest in answering. And shows a typical ALSE's prediction pipeline, which I think is also a standard nowadays, more standard machine learning model training pipeline. Right? So we start with a group of people that are of interest, and we extract the features and labels for this group of people. So the label here means the outcome. Assume we're talking about binary outcome here, then the label is just binary. Then we split this data into a training set and test set. Right? We're doing this so that we do not overfit our models. It is important to assess how well your model performs on the test data set. Then on the training set, we fit a bunch of machine learning models. We can do cross-validation to pick the best hyperparameters. And in OHDSI, in the 2 stack, we have almost all the most popular machine learning models that you can pick, from simple linear regression, regularized regression, to tree-based methods, to neural networks, k-nearest neighbors, ensemble and deep methods, you name it. They are there. And I linked the name of the key open source packages we use are also linked below on this slide. Then once we're done with the model training, then we can take those models that are well trained and do prediction on the test set or the incoming new data. And we can assess how well the model performs. And there's a lot of evaluation metrics that we can assess the performance on. For example, sensitivity, specificity, precision, recall, F1 score, and we can also assess the performance using plots like RC plots, precision recall plots. So if you have some experience in machine learning, this, I hope, is not new to you. And this is just a screenshot of, I think, the patient level prediction package, just showing all the classification models that we have to do binary prediction. And also, we also have the Cox model ready if you're interested in survival outcomes. This might be outdated. I'm not quite sure. I take it from the manual, but I hope that gives you enough choices to at least get this started. Yeah. And we also build, once you're done with model training and prediction, you want to look at, well, then how well do my model performs, right? Our algorithms spit out a lot of spreadsheets, tables. It'll be easier if there's an app that will allow you to visualize those, right? Who doesn't like to look at plots rather than reading from tables? So we do have Shiny apps ready that can take the output from our algorithms and to present them in a much more human-friendly format, like this, showing the sensitivity, specificity, the all kinds of plots the model generated, and also we also provide a table, why not? And we make it a little bit nicer so that you can compare across many models and the different setup that you have chosen. All right, that's also a very quick overview of patient-level prediction. Let me pause here and see if there's any questions. Are y'all good? Are you awake? Thumbs up if you're awake and you're good to go to the next session. All right, and have your thumb ready because there will be pop-up quizzes in the next 20 minutes. And you have to pass that in order to have the break after this. All right, so let's now talk about population level effect estimation. That's where I spend most of my time. That's where I did the topic that I did my PhD in, so I'm really excited to talk about it. Let's begin with an example study. Does chlorothalidone reduce risks of cardiovascular outcomes more than hydrochlorothiazide? All right, that's a lot, right? It's very mouthful, especially those drug names. So let's unpack this question. So questions like this can be translated into this boilerplate. So basically, we're comparing risks of a health outcome between a target treatment and a comparator treatment during a period of time at risk. So in my example study, the target exposure is chlorothalidone. The comparator is hydrochlorothiazide. And the outcome of interest here is a composite cardiovascular outcomes. For example, hospitalization for acute myocardial infarction can be one. And the time at risk, this question on the top of the screen didn't quite say, but in practice, we typically do either own treatment or intend to treat, or the risk window can be ends at treatment discontinuation, like the end of the drug era, or it can also be the end of the observation period of a patient. So those are different choices. Happy to go into more details if you're interested, but for now, I've just mentioned those are the typical options that we have in the study. So our task here is to estimate the causal effect of drugs or the relative causal effect of drugs from observational data. Throughout the years, OHDSI community has done a lot of population level effect estimation studies. Some of them are about hypertension. These are some of the examples, papers that the community has published in Lancet, hypertension, and JAMIA. And also over the years, through many practices, working on studies one after another, the community has developed a framework with core principles that we think highlight what best practices of doing observational studies should look like, how to make the studies more robust and reliable and reproducible. I'm not going to read them all out here, but just to highlight that overall, we emphasize the importance of open science, like published study protocol, pre-specify analysis design, so later on you cannot cheat in your analysis. We advocate for systematic diagnostics. We advocate for open source softwares, and also we strongly advocate for publishing all study results, not just the statistically significant ones. So this is a real-world evidence generation pipeline that OHDSI has put together. At every step, so we have from the very beginning data quality evaluation. There's tools for conducting database diagnostics. There was a question from the audience earlier today asking about diagnostics at database level. So we have data quality dashboard, DQD, or Achilles. Those are package names that can help you to assess the quality of your database at the database level. Then we also have cohort diagnostics, such as Phi Evaluator or Phoebe, that can help recommend concepts to include in your phenotype algorithm, and then to assess the quality of the data in a specific cohort of interest. So I'm not going to go over them here because of time. I will be more focused on the diagnostics and the models that we typically use in analysis stage. And so that's the third, the lower light greenish box on the screen here. So that's what I will be focusing on. And at each step, when we run those diagnostics, some studies will pass, some study will fail. And for those studies that fail the diagnostics miserably, then we may discontinue the study, or we will really have to interpret the results with caution. So in OHDSI, not all studies get to the finish line. So that is an unfortunate hard truth, but I think it's good for, improve the overall quality of real-world research and real-world evidence. So if we're talking about causal inference, I cannot not talking about what is confounding or confounder. So if this is the first time you hear about this word confounding, confounder, or confounding bias, let me just give a very intuitive example here so that we are all on the same page. Confounder is bad. Let me begin by saying that. And why is it bad? Let's imagine if we're doing a study, we are interested in whether carrying butane lighter causes increase the risk of lung cancer. If I look at an observational data, people who are smokers are more likely to carry built-in lighters around. And we know now scientifically that smoking causes lung cancer. So if I'm doing a simple association study between built-in lighter and lung cancer, I will find that people who carry built-in lighter around are more likely to have lung cancer, as if built-in lighter have a causal effect, causally increase the risk of lung cancer. However, we all know from common sense that cannot be the case, right? This is not true. But why we observe that association in the data? That's because there's a confounder smoking status in this study. So without adjusting for the status, smoking status, we're not able to get to the right causal conclusion. And that is why adjusted for confounders are important in observational studies. In randomized controlled trials or RCTs, you don't have to worry about it because the treatment is randomized to patients. So smoking status will be balanced, between the people who got the treatment and people who didn't. However, in observational studies, because the treatment is not randomly assigned, there will be a lot of confounders, things that distribute differently between the target cohort and the comparator cohort. So that's causal inference or confounding bias within 1 minute. So how to adjust for confounders, right? In a study, there's a lot of confounders, and more problematic is that we don't know what confounders are. Like we don't have the complete knowledge about what variables are confounders in a given study. So in OHDSI, we use this large-scale propensity score approach, or LSPS. We adjust for a large set of covariates, almost all the concepts in OMOP CDM. The difference that we do compared to others is that we don't rely on human expertise to select confounders. We just adjust for all pretreatment covariates. And there are some variables that we know from the causal inference literature that we should not include, like instruments or unbiased colliders, and we have ways or heuristics to avoid that. Happy to discuss that offline. So LSPS is, in essence, it is regularized lasso regression. And we use regularization to avoid overfitting, because most of the times we have fewer patients than number of covariates in a given study, right? So our covariates is almost always at the scale of like 50,000. But in a study, we may only have a few thousand patients. So that's why we do regularization. Once we estimate propensity scores, we can use it in different ways, like propensity score matching or stratification. And the goal there is to adjust for confounders, right? Remember that smoking example that I gave? After adjustment, we hope that variables like smoking status or like all variables are balanced between the target and the comparator cohort. And then we apply, but still, right, even though we adjusted for all those covariates, we still worry about residual bias, right? How valid is my study? Then we have a set of diagnostics that we screen our studies against those diagnostics, and that will tell us how valid is my study. And I will go through them one at a time. Now, the quiz is coming up, so be ready. Diagnostic 1, equipoise. So this diagnostics tells us how similar are the two exposure cohorts. So if this equipoise is too small, this value is too small, then that means the two cohorts are too incomparable, meaning if I'm doing propensity score matching, it's hard to find a match for the patients, and that can lead to unreliable estimate. So our typical rule is to have, if a study have equipoise larger than 0.5, then we'll feel much comfortable with the study. And the equipoise is defined as the number of patients or the proportion of patients with a preference score between 0.3 and 0.7. So maybe easier just if we look at this figure on the slide to understand what this means, right? So the x-axis is the preference score. You can think of it as the propensity score. It's a transformation of propensity score. The y-axis is frequency, right? How many patients? So if the higher the curve means the more patients with that preference score, right? So it's like a histogram, but stratified by the treatment group. So blue is, let's say, the control group, the comparator group. red is the target group, and we show the preference score for them. And we want most of those to concentrate between 0.3 and 0.7. Oh, so can somebody, I thought I included here, but maybe this is not the latest version that I worked on last night. That's okay. Can somebody tell me on this slide here, if this is a plot from your study, does your study pass the equipoise diagnostic? Thumbs up if you think it passed the diagnostic, thumbs down if you think it doesn't pass the diagnostic. What is your answer? Thumbs up, thumbs down. It's a tricky one, I can tell. Yeah, I would say maybe it's borderline, right? When we look at it, maybe about 50%. So this may or may not pass the diagnostic. So those who, with your thumbs that's like this, you got the right answer. Good job. Okay, so this equipoise tell us, before we do any adjustment, how similar are the target and comparator cohorts. The second diagnostic we have is covariate balance diagnostic. So it tells us how similar are the covariate means between the two exposure groups. And if it's too large, then if it's too large after adjustment, then there's a risk of residue bias. So we use a cutoff of standardized mean difference of less than 0.1 to indicate pass of this diagnostic. And we assess covariate balance on all 50,000 covariates. So on the right, on your left of the slide, it shows us example plot of a standardized mean difference plot. So each dot on this plot is a covariate, for example, smoking status. Right? It would be a 1 dot on this plot, or age, pre-existing type 2 diabetes. So all those concepts will be represented as a dot on this plot. The x-axis is the difference of that covariate mean between the target and comparator groups before any adjustment, like before propensity score matching. So on the x-axis, we all see the values can be from near zero to have a very high value. That's okay. What we care about here is that after propensity score matching or after your adjustment, the y-axis shows the covariate mean difference after adjustment, and we want that value to be very low, to be near zero. So, and here the red horizontal line highlight where the 0.1 cutoff is. So we want everything to be below the red line. Then that indicates a good covariate balance and a good study, essentially. All right, there's a question.
There's a really good question in the chat, so I'm going to say it out loud. Can you talk a little bit about, are covariates hypothetical, or are they determined by expert decision?
Yeah. So the question is about whether the covariates are determined by experts or domain knowledge, or is it sort of automatic? So the answer is it is automatic. We suggest not do covariate selection based on domain knowledge because we find it is unreliable. If you look at published observational studies on the same research question, we often find that they select the different confounders, right? They have some in common, but they also have a lot of discrepancy among what variables are confounders. So in OHDSI, we do large-scale approach. We do not select confounders manually, or meaning based on domain knowledge. Yeah, so this is a covariate balance plot from a study. So you can tell from the slide, it's good, so it's a thumbs up. Can I get a volunteer from the audience why this is good, why this study passed this diagnostic? Or you can now just speak up, I can hear you, why this passed the diagnostic? Excellent. And we're looking at the y-axis, right? Yes, so this passed a diagnostic because the after adjustment, meaning we will look at the y-axis, all the dots are below 0.1. So meaning we achieve good covariate balance after adjustment. And why this is bad, I think I will answer that myself, because now you see a lot of dots that are spread around, right? That has a Y after adjustment covariate difference much higher than 0.1. So those are highlighted in the red box here. So now we come to the third diagnostic. The third diagnostic is called expected absolute systematic error, or E-score. So this is the score that helps us assess residue bias in the study, and it can be estimated using negative controls. So what is a negative control? So negative control is an exposure and outcome pair where the relative risk is believed to be 1. Meaning, for example, ingrown nails can be a negative control outcome for a hypertension study, a study where we investigate the effect of antihypertensive medications, right? We don't believe any of those medications has a causal effect, either increase or decrease the risk of ingrown nails. So this is one example of a negative control outcome. And in OHDSI, we uses 50 to 100 negative control outcomes for each study. And we do select this based on automatic algorithm that screens all the PubMed literature to select those negative control outcomes. So it is empirical. It is based on empirical knowledge, but we try to do it systematically across a lot of literature. And we can also use those negative control outcomes to generate synthetic positive control outcomes so that we can assess the type 1, type 2 error and all those good statistics. And the way to rate, so almost every diagnostic comes with a plot. That's how we try to make this easier to interpret and more user-friendly. So this is a plot showing the plot all the negative control outcomes, where each dot is a negative control outcome. We estimate the effect of our drug of interest on that negative control outcome. And the x-axis is the estimated effect size, and the y-axis is the standard error. And the two diagonal lines indicate where the p-value equals 0.5 would be. So those two orange rectangles on the slide indicate the areas where an effect estimate will be considered statistically significant. So what does it mean for a negative control outcome to be in the orange triangles? It's a false positive, right? Because we believe there should be the causal effect should be none, should be 1. In this case, we're doing a relative comparison. And if the study indicates that there's a significant causal effect, then we know that is a false positive. And if we observe a lot of the negative control outcomes show up in those bottom left and bottom right triangles, then that indicates the study has a substantial residue confounding, residue bias. So this is showing what a good E-score plot should look like. So the top is the pre-calibrated one, or actually the bottom is the uncalibrated one. So, but anyway, this is why this is good, because before calibration, the plot looks almost the same. And when we look at the E-score here, it's 0.01. So a small E-score close to 0 means there's a little residue bias, and we're good to go. And all these plots will, we have packages that will output those plots for you, so you don't have to manually code those plotting functions. And so this will be after the break, when Jenna introduced open source analytics, that's where you get to do some hands-on experiments with all the packages that I mentioned. So my part of the talk will be just a conceptual, explain what conceptually those methods mean. Right, so, and this is bad when a study failed the diagnostic. So if I flip back and forth, you can see the difference, right? If you look at the plot, this one, the bottom one, before calibration, we have a lot of dots that are in the lower triangles, meaning that we have a lot of false positives, and that indicates to us that there's likely some residual bias in the study. It could be all the way from, you miss certain concepts, your database does not have certain concepts recorded, or the cohort definition need to be revisited, and this is, that's what all these diagnostics are for, to tell us, maybe we should revisit some of the previous steps of how we conduct this study. And if after those reviews, if not, you still think that that is right, then that just means maybe this isn't a good question for doing observational research on. Maybe we need some trials or experiments to really understand that.
Can you help the audience interpret the hazard ratio with the tight confidence interval on the bottom to the calibrated hazard ratio that has been indeed reduced but has a much wider confidence interval on the basis of that plot above?
Yeah. So before calibration, if you look at the bottom of this slide, I include here the hazard ratio before calibration is 5.55, and that's the lower and upper bound for this hazard ratio. So the interval is about 6, I would say, somewhere around there. Too early for me to do math on spot. Then after calibration, this is the calibrated hazard ratio, but with a much wider confidence interval. And this is what we will see this happen when when the negative control outcomes are like this, when there's potentially a lot of residual bias in study, then essentially our calibration account for the fact that maybe we're not so certain about our estimate. So empirically, that's what we see, is that after calibration, our estimate, the confidence interval is much wider to account for that uncertainty. Hope that answers your question. Yeah. And thank you for that great question. That connects very well to this slide, is what do we do in that calibration? There's a lot to go over, a lot of math to go over, so I think it will be more suitable for an advanced OHDSI tutorial. But here I will just give this very simple analogy. Imagine if you have a scale and you put a standard weight on a scale, a standard weight of 100 pounds, and your scale tells you it's 126 pounds. So what would you do if you weigh a bag of apples on the scale? You would do calibration. Right? You know, okay, this scale is probably overweight by 26 pounds, and when I do calibrate, when I weigh something that I don't know the true weight, I will do that at calibration by subtracting what the scale tells me. Subtract that by 26. So that is essentially intuitively what empirical calibration does in our analysis. It readjusts our treatment effect estimate based on how much residual bias we think is in the study. I think this is the last diagnostic I have, called the minimum detectable relative risk, or MDRR. This is essentially a statistical power analysis. Oftentimes, if we're running a trial, we do a power analysis to get an estimate of how many participants we need to recruit for our study. Here in our case, since we're doing observational study, meaning the data is already pre-collected, we think we reformulate this question to ask, given the available data, what effect size would the analysis be able to detect? Since we already have a fixed sample size, and if we pick a significance level of alpha equals 0.05, then as you can imagine, we can calculate with some math, like how strong an effect size need to be in order for me to detect that in the data that I have. And when MDRR is close to 1, then that indicates where the study is well-powered. For example, MDRR equals 1.75 means we have the ability to detect 75% increased risk if present. Right? In this case, meaning if lisinopril has an increased risk by 75% compared to hydrochlorothiazide, then my database will be able to detect that. And when it's bad, you will see MDR that's very high, like 6, 17, 27. Right? What does it mean? The study is not underpowered. The study is underpowered because I need the target to have 600% increased risk in order for me to detect that in my database. Right? That's what MDR equals to 6 means. And this shows a published study how those models and diagnostics that I mentioned come together to play, to how those actually work in a study. And these are the plots that I've already walked you through. So after you do all those, you fit all those models and run those diagnostics on your local database, and if that pass all the diagnostics, great, woohoo! Now you're ready for the network. You're ready to contribute your data and your analysis to the network for meta-analysis, right? So now how we're going to combine those evidence from each individual database into something that's a global, a network level estimate. There's a lot of tools we use, but overall we use likelihood-based meta-analysis, and we can also do calibrations at the stage to further correct for bias. So I will keep it brief here, because that also by itself, I think, worth several hours of discussion. After we do a study, we remember one of the largest principles that we want to make the results publicly accessible to improve transparency and reproducibility. And we have Shiny apps for that. I think later today in our tutorial, our other faculties will demonstrate what it looks like. So I will skip that here. And that concludes my talk.
Okay, I realize it's a short break, but we do have a 15-minute break. I do believe there'll be coffee outside, so please go stretch your legs. And we are going to start right at, does it say 10 o'clock? 10 o'clock.
So before the break, you heard about the OMOP CDM and the standardizations, and you also heard about the different methodologies that we implement in OHDSI. I'm now going to be giving you a brief overview of the open source tool stack that we've developed and actually show you how you can use that to run a network study. And then after, Daniel will actually show some of the results we've got from running these tools to do a network study. So just to give you a brief overview of how this all fits together, all of our tools require you to have your data mapped to the OMOP CDM, and that standardization enables us to create standardized tools. The tools generally require you to have a study population defined. So we use Atlas to create that study population, what we call a cohort. So this is a set of patients that have some either medical condition or drug of interest with some inclusion criteria, and it has a period of time that you're going to follow them for. And then you can use the Hades tool stack, which has an R front end. So for those of you who know programming languages, R is a statistical programming language. We use that as our front end, but behind the scene, we also use a lot of other programming languages. So you often see Java, Python, other languages. It's all open source, and it's all available at github.com/OHDSI. So if you go to that GitHub repository, you'll find the code for all of our packages, and you can actually contribute to that. So if you're someone who's a coder, not only can you use the tools, you can also contribute, and you can suggest improvements. And we're improving these tools all the time. So I'm going to give a brief overview of Atlas, a brief overview of the helper tools, what I call them, and then I'm also going to show you some of the characterization, estimation, and prediction tools. And these all use the OMOP CDM and the cohorts that you'll generate through Atlas. So let's just go into Atlas. What is Atlas? Atlas is a friendly website that you can use to create logic with code sets, as you heard earlier today, the standard vocabulary, to identify a set of patients of interest. And I've got some example here. I Googled cohort, and this actually picture came up, and I thought this was very suitable. So here you can actually see 3 examples of different cohorts that you could generate with Atlas. So pregnant women, you could identify code sets and logic to identify pregnant women in your data via Atlas, and you would have at some period of time, it could be while they're pregnant, it could be some period of time after pregnancy. That's an example of a cohort. Children under 5, that's another example of a cohort. You would need some index. It could be the first visit, outpatient visit they have in 2020, and you could be following them for a year. It's another cohort you could define in Atlas. And then men with HIV. So this could be at the start of their diagnosis, and you could follow them for the whole observation in the data. So these are 3 examples of cohorts that you could create with Atlas in a friendly way. And the nice thing with Atlas is that it enables you to define these cohorts without actually knowing SQL. So if you have your database, but you don't know SQL, Atlas will create the SQL for you. And so it makes it very friendly. And we try and make our tools as friendly as possible, even for those who don't know programming. So just to give you a little bit of an overview of Atlas, the picture on the left-hand side is a screenshot of the public Atlas. So if you're interested, you can actually, everyone here has access to this public Atlas. It's atlas/demo.odyssey.org and that's the address. So you can see I don't know if it's big enough, but there'll be some links in the slides that you'll get later. So the side of Atlas, you can see that there is the home. If you go to Atlas, the first bit you'll go onto is the home. Then you have the data sources. The data sources is actually quite nice. That lets you explore the vocabulary. So you can actually, that lets you explore the summary of your databases. And then the next one is the search. So the search lets you explore the vocabulary. So you can actually type in some string, press enter, and it will actually search through the names of all the vocabulary to show you matches. So I've got an example here where I type lisinopril, and then on the right-hand side, you actually see the results that come back from that. So we've actually got the third column is the name. This actually is anything that has that lisinopril matching will show up here. And I happen to order this by the 6th column, I believe it is, which is DRC. This is the descendant recode count. So this is how many times that code or a descendant was found in the database. So this is actually telling you this is quite a popular code. So you can actually use Atlas to search through the codes, and you can actually create concept sets, which brings me on to the next example. So now you can see I've moved down. You can see I've actually selected on the left-hand side the concept set section. And in there, you can actually select all of your codes of interest. So it's kind of like a little bit like a shopping basket. You select it on the search, and you can bring it into your concept set. And this actually is quite nice. It lets you explore a lot of the vocabulary. You can see that I've actually picked in lisinopril, and I've said I want all of this is an ingredient code, and I want all the descendants. And this actually is identifying over 3,000 concept IDs in there. So I can actually move over to the other tab and look at those. And I can even look at the source codes. So it's quite nice. You can see from your concept set what source codes you're actually bringing in. So you can say, what ICD-9s and ICD-10s would this have basically been capturing in my data? So concept set is one of the first components of a cohort. The next bit is creating that cohort. So you have a cohort definition option. And in there, you can actually specify now how you're going to be using your concept sets with the data. So I'm looking for a drug exposure. So this is going to go to the drug exposure table, and it's going to find anyone who has a record of lisinopril or descendant. So I'm actually going to be capturing every single exposure of lisinopril in the data with definition. And I'm looking at every exposure. You have options to look at things like first exposure with at least a year in the data, first exposure when you're above 18. So there's lots of other inclusion criteria you can add. But this is a nice, friendly way of creating your cohorts. And these are key for the rest of the analyses. You need cohorts to run characterization, estimation, and prediction. I've got a couple of examples here, so feel free to play with this later when you get your slide deck, or if you want to go to the public atlas now, you could actually go through and look at some of these examples. So I have an example for lisinopril, and I have an example for cardiac arrhythmia. And you can play around as much as you want and add any inclusion criteria you want and just get a feel for how you can actually define a cohort in Atlas. So I've talked about the standardized data and about the cohorts that you need for our tool stack. Now we're going to focus on the HADES tool stack. So for those of you who know R, you've probably come across the tidyverse, which is a collection of packages that work nicely for playing around with data. HADES is the OHDSI equivalent of that. So HADES is a set of tools that we've developed open source that let you do the characterization, the estimation, the prediction at scale. And also you can run network studies very efficiently with these tool stacks. So you may be wondering why use HADES, or why not use the tidyverse or write my own code. The advantage of HADES, in my opinion, is that it's built for the OMOP CDM. So it goes from the OMOP CDM to results. It makes a very streamlined pipeline to do the analysis. Secondly, it implements best practices. So in OHDSI, we're constantly running methods research to find best practices. When we learn a best practice, we then integrate it into our tools. So you can be sure that you're doing the best practice at time, whether it's for causal inference, prediction, characterization. And you saw that for causal inference, we have a lot of diagnostics. These are implemented in our tool stack. So we're actually looking at the quality of the analysis when we're running it. The other thing is that our tools are developed to handle big data. So I'm going to show you some helper packages that let you analyze big data with a very basic computer. And so our idea was that we wanted everyone to be able to analyze and use our tools, even if they have a very basic computer setup. The last thing is that we have a federated data network structure in OHDSI. What that means is that everyone has their own environment. So everyone has a different database platform. Some people can have Mac, some people can have Windows as their operating system. It's very diverse, and we've created tools that will work across different environments, which enables the network network studies to be executed. So we've made it very streamlined and easy to do a network study with these tools. And that's why I would say that you may want to think about using HADES. There's information on the website, so you can actually look at all the different R packages, all the different tools that we have. I'm just going to highlight a few of them. So there's 5 key supporting packages that I use all the time. The first one is Database Connector. This package lets you connect to your database, your OMOP CDM database within R. So it uses a Java backend, but you can write SQL statements, execute it to the database, and get the results returned. So if you're doing analysis in R, Database Connector is key. Whether you use the rest of the HADES or not, it's nice to bring that data back as a data frame. You want to use Database Connector for that. SQL Render. This is a tool that lets you translate between different SQL packages, or database platforms, sorry. So if you've got someone's using Redshift, someone's using SQL Server, someone's using Databricks, they all have slightly different ways of writing a SQL statement. So we needed a way of translating between those so that when you run a network study, you can actually get the SQL translated depending on the environment. And that's what SQL Render does. So it's this is key really for a network study because everyone has different environments. Feature extraction. This actually links back to a question that was on the Teams earlier. Or actually, I think it actually may have even been asked in person about the covariates that we use. So feature extraction is a package that at a point in time and for a set of patients will extract up to thousands of covariates, attributes, features. They all mean the same thing for a patient. So it could be their age index. It could be an age bucket, like are they 0 to 4 index? It could be, did they have this specific diabetes code in the last year? It has a library of features that you can select from, many, many of them. And this is why a lot of our tools use data-driven features because they're using feature extraction to extract the features. And generally what we do is we extract a feature per condition code or per drug code that's happened in any of the patient's pasts. So you can end up quite frequently with 30,000 to 50,000 features from feature extraction. And you have the option of which features you select. Andromeda is a package that's really useful because we're dealing with big data. So R has a little bit of an issue where when you're using R for analysis, it puts all the data into memory, into its RAM, which means if you've got a computer that has 4 gigabytes of RAM and you're trying to extract data that's 5 gigabytes, R is going to fail. Andromeda is our solution to that. So rather than selecting the data into RAM, we actually have an option of selecting from your OMOP CDM into a local SQLite database on your laptop, and then you communicate through R to SQLite. And that means you don't need all the data in R, so you can handle big data sets, and you can still do the analysis in R. So Andromeda solves the big data issue. Eunomia is a really nice package if you're a developer, because it actually has a synthetic OMOP CDM database. It generates it locally on your computer as a SQLite, and you can actually test code, and you can test methods with Eunomia. So if you're someone who doesn't have data, but you're wanting to do software development, or you want to create a network study, you can still test out your code with Eunomia. So this makes it nice and friendly for everyone to use our tools. But the 3 main things that most people want to actually do as an Odyssey community are characterization, causal inference, or prediction. We want to analyze the observational data. So we actually have lots of different packages for doing this. For characterization, we have the characterization package. This lets you describe the cohorts you're interested in. So you can look at aggregations of the features. What is the mean age in this cohort? How many of these patients had this specific diabetes code in their past? You can compare across databases, across cohorts. You can look at, if you have an outcome of interest, you can look at the timing. When did that outcome occur relative to the start of their target cohort? So if they had lisinopril, when did they have the cardiac arrhythmia? Was it before? Was it after? You can look at that timing. So there's lots of different characterization studies. You could look at risk factors of the cardiac arrhythmia in the lisinopril user. So that's what characterization will let you do. Coincidence, as the name suggests, looks at the incidence rate for the outcome in the target population. And these have been created so that they're very efficient. You can actually generate. Chris Knoll, who's actually a guest, I guess, in this meeting, he actually has created the cohort incidence package, and he's made it very, very efficient. I don't even know how he's made it as fast as he has, but it runs very fast. Causal inference, we have cohort method. We saw the actual methodology earlier today, but we can actually implement that, and all of the methodologies that you saw at scale. Again, it's very easy. Same with self-controlled case series. So you can run causal inference as long as you have your target cohort, your comparator, and your outcome. You just have to specify a few settings. Patient level prediction, this is what I tend to focus on, so I know this one pretty well. This one lets you train predictive models for an outcome of interest within a target population for some period of time. And we have a lot of the state-of-the-art classifiers in that package that you can pick from. You can also add customizations if you want and put in your own classifier. And then we've also created this deep patient-level prediction that has quite advanced deep learning models. So these will actually let you do very advanced prediction models very easily and very readily, as long as you have your data mapped to the OMOP CDM and you have your cohorts. 2 packages that aren't quite in Hades, but I wanted to kind of give them a shout out because they're going to be in Hades very soon and they're very useful, is Strategist. Strategist is, if you want to create a network study, you'll want to use Strategist. It lets you create a shareable JSON object representing your study design. And this means that you can get someone to run a network study by just giving them that JSON. And then Strategist knows how to read that JSON and execute it as long as you point it to the OMOP CDM database. So Strategist has made it very, very easy to do network studies. And we've learned a lot over the years how to make this process more efficient. And we've decided that a JSON script makes it the easiest way to share the study. Strategist also manages the environment. So in R, people can have different versions of packages. They can have a different setup. Strategist makes sure that you can create a virtual environment that has the setup we know will work for this study. So it also makes it more reliable. You're likely to run that study without any issues. So Strategist is helping us do network studies very easily and at scale. I have an example here, which I'm actually going to show you. So This is a GitHub repository. So, this is what I open. Okay, I might have to copy it. So this is I should have got this link already. There we go. So persistence. So if you click it enough, eventually it opens. So this is a GitHub repository where this is the kind of standard approach we do for network studies. We create a GitHub repository. Oh, isn't it?
Oh, very weird. That's not. We need the AV guide.
We could copy and paste and try again. It was changing earlier, right?
Yeah, it was changing earlier. Here, how about I do this? How about I exit out of here? Okay, there. And then you'll just have to share again. I don't know what's...
Okay, so in the OHDSI Studies GitHub is where you'll find all of the study repositories for network studies. And I created a tutorials demo 2024. And this has all the code to create the settings. It has the settings itself, and it even has code to create a protocol in here, which I'll show you in a bit. But I'm not going to show you the code because a lot of people don't want to see code, and I'm not going to put you through that. But if you're interested in seeing the code, there is a settings.r file that you can actually look at what was needed to create the specification for a study. But the main thing is this analysis specification JSON. So this is a JSON object that contains a full specification that will know the SQL for the cohorts. It will know how to do characterization that I want to do. It will know how to do the estimation study that I want to do, and it will know how to do the prediction study I want to do. And someone can just take that JSON, download Strategist, execute with this JSON by pointing to their database, and they'll be able to run the study that I've designed. It will output CSV files that you would want to explore, and I'm going to show you actually how to explore it nicer than CSV files. And once you've explored it and you're happy, you can then share that result with the person who's actually designed the study. That will get aggregated, and then they can get a paper. It's so easy to run a Strategist study now. So all you have to do is say, where do you want your results saved? You need to specify the connection to the OMOP CDM. So if you don't know the connection, you want to speak to the database administrator to find out the server, the user, the password. But once you've got that set up, you specify that here. And then you don't need to edit below the line, you just cut and paste. So you cut and paste, and what this is going to do, it's going to download the analysis specification JSON, and it's then going to use Strategist to execute it. And you're going to see it going through. It will create the cohorts for you. It will start running the cohort diagnostics, so you can look at phenotyping. It will start running the characterization. It will start running the estimation. It will start running the prediction. And then you'll get your results as CSV files. So it's super friendly now to do network studies via Strategist. Yeah, sure.
That looks super interesting. Is that really designed for just network studies, or is this going to be part of kind of a reproducible analysis pipeline package as well? Because that's the first thing that I kind of thought of with that.
Yeah, no, that's a great question. So I am selling it as for network studies, but actually it can be used without a network study. So if you just want to do these analyses yourself, you can use Strategist. And it's actually, Chris actually would suggest doing that. I'm someone that likes to use the individual packages, but I know we've had arguments because Chris thinks you can just use Strategist for everything now. So yeah, it's probably best practice to use Strategist for any study. So I'm just finding there we go. So I won't go into full screen because I'm actually going to click off that again soon, and I'll try and avoid the issue we had before. So that Strategist lets you easily do network studies or just a single study because it will let you do all the different types of analyses in one execution, which is quite friendly. The other thing is the protocol generator. So when you're doing a network study, you generally need to have a protocol to say what you're going to do. And people will take this protocol to base their IRB approval on, And people want to know, what am I running if I'm running it? They don't want to look at the JSON spec and try and figure it out. So the protocol generator will actually create a human-readable form of that specification so you can see what was done. So I've got the code for creating the protocol generator in that GitHub. So you can go to the GitHub protocolcreation.r and you can see it's 4 lines of code. It's simple, pretty simple. But the main thing is actually looking at what does the protocol look like. So this would generate in about, actually that didn't work. Luckily I've already got the link here. So this will generate in about a minute. You put in your JSON spec, you run the protocol generator, and it will create this HTML file. And in this HTML file, it will actually tell you information about what research methods you were using. So I'm calculating 10 different incidence rates. That's being done for 5 different target cohorts, 1 outcome, and 2 time at risks. I can click to see what is the human description of the cohort of interest, and it tells you this is what you see in Atlas in your human friendly format when you create the cohorts. So it replicates that here, so you can actually look at what the logic that you use for the cohort. And then you can scroll down and it will tell you how you're doing characterization, what targets, outcomes, time at risk, and settings you put. So this is kind of the feature extraction covariate settings. And then it will tell you I'm doing cohort method, and this is my design for cohort method. And I'm also doing patient ill prediction. And I'm going to develop 2 models. And if I want to, I could look at the design for each model. So here it's just a human readable form that you might want to share. You could also write your own protocol if you want, but this is a lot quicker. Okay, I'm going to stay on this just because it makes it easier. And then the next thing is the viewing the results. So I kind of said that you have this situation where you generate a lot of results through OHDSI. And it's nice in many ways that you can generate results very easily in OHDSI, but sometimes when you're the person who has all these CSV files, you don't know what to do with them. So to help with that, we've created 2 Shiny packages. And Shiny is a R tool for exploring results through a website, and you can explore interactively. So we've created an interactive website for exploring all the results that we generate with our tools. So I'm going to click on get this demo working. I think I need to copy and paste it. Oops. This is where there's issues with Mac and Windows. Our tools support it, but my brain doesn't. Why is this not pasting? There we go. Okay, wait, is that the wrong link? Did it copy it? Okay, let me copy. So this is an example. Okay, paste. Hopefully this will happen. So this is an example Shiny app that's on the OHDSI Shiny deploy server. So this actually is a way, if you create a network study, you've got results, you can actually deploy an app in the same way that I've done it here, and it will be accessible to anyone you give that link to. Here I've just got an example of what the Shiny looks like. So the first thing you'll see is we have an about, tries to kind of ground you to what the app's doing. Then you've got a data source. You can actually look at what databases were used for your network study. And we see here that I've just run this on one database. So we just have information about that one database. If you did a network study, you may have 10, 20, 30 rows here for different databases. And it will tell you the version that was used, the OMOP CDM version, and so on. You also have a view for the cohorts. So for each database and each cohort, it'll actually tell you the cohort name and how many people you identified in that database. So here we've got the one database, Medicaid database, earliest event of essential hypertension. There was over 5 million people that we identified in that database. And we have this for every single target cohort and outcome and comparator. Cohort diagnostics, I didn't really go into this too much detail, but this is actually a package that we have in Hades that lets you explore phenotypes. So we often use this in our phenotype process to see if the definition we've created seems valid. So you can explore that in your own time, but there's a lot, so I'm not going to go into that. Characterization lets you do that description, so you can look at the risk factors, the time to event. But the thing that you're probably most interested in is the causal inference. So I'm going to click on estimation, And I'm going to pick lisinopril, cardiac arrhythmia, select that, and it's going to come and tell me that there was 2 different estimation designs done on this database, Medicaid. And the first thing it tells you is, did you pass diagnostics? So you heard earlier about the diagnostics that we implement. Here, it will just tell you, did you pass or fail? If you want to look at why you passed and why you failed, you can actually add on the different diagnostics that are actually executed with the OHDSI tools. And it will actually tell you the values, and you can see that we were pretty well powered, and we obviously matched, we did pretty well on the matching and so on. So we got 2 results, and if we go to the results tab, we can actually look at what those values were. So we get the analysis name. So the first one, we actually did propensity score matching. The second one, we just did a very basic outcome model. You can see what the uncalibrated relative risk was and the confidence interval. And you can look at the calibrated relative risk and the confidence interval. So this will actually let you see whether there was a causal effect, evidence of a causal effect or not. And you can even expand into this, look at the results, and you can actually look at some of the diagnostics that were shown earlier. So if I go to propensity score, you can see this propensity score plot that we saw. So this is a nice tool for letting you explore the results in an efficient way. You can create this locally before you send to the data partner, or you can just wait and look at the CSVs, and then the data partner can create this app for you. So let me go back to full screen. And this app's available for you to explore if you're interested in playing around with this after this presentation. If you're a software developer and you're interested in contributing, we're always happy to have more people contribute to our tools. There's lots of guidelines on how you can do that. So if you go to the Hades, odyssey.github.io/Hades, you actually see there's a whole section for developers telling you how to contribute and guidelines for actually contributing. So hopefully I'll see some of you were interested in the next Hades school. And then here I just want to show you how you can use our tools to do a network study efficiently. There's a tutorial later today that actually will go into the network study more. Is there a question?
Just a quick question. Do you show one of the cohorts you created? Do you mind talking a little bit about the time that it takes, that cohort? I know there's a lot of factors impact that, but just I'm wondering about the time it takes to create a cohort.
So that's a great question. So it really depends on the cohort. Drug cohorts, in my experience, tend to be a lot easier because it's often you just find that lisinopril ingredient, and then you just say anyone who has that for the first time is my cohort of interest for cohort method, for example. So for that, it's pretty simple. For conditions, it can be really tedious and hard. Like that is probably the majority of the work. So once you've got your cohorts, the rest is fast, but creating the cohorts takes a lot of effort. But we have a lot to guide you for that. So Atlas will let you search the vocabulary. You saw Athena, it lets you do the vocabulary search. There is as long as you have a more recent version of Atlas, there's a recommender tab that tells you might have missed this code from a concept set that helps speed things up a little bit. And then once you've created your initial cohort and you run cohort diagnostics, sometimes that will show you that you've got some errors and you might have to revise. So sometimes it's an iterative process, and it can take a lot of time. And I'm quite fortunate. There's other people in the team that do the phenotyping, and I do more of just plug them into to the framework for the analysis. So I don't know if you've got more comments, Erica, on the phenotyping.
No, I think that's good. But was your question about time to generation?
Oh, sorry. Oh.
So, well, I think what Jenna still said applies. Some cohorts can be very complicated. So, for example, one of the cohorts I'm working on right now that will be available in the OHDSI community soon is how do you find pregnancy episodes? So in a given database, there can be millions of women who have pregnancy episodes. So for example, if you run that, it can take a while to get through everything. But then like Jenna said, like something like, I want to just find all the patients exposed to lisinopril, depending on your environment, that could take seconds. But again, it also depends on your environment as well, like how well it can do those queries. But I would say it is very efficient.
Yeah, generally, it really is environment dependent. So we have a good environment, we have good indexing on our databases, and we have a good database platform. So for us, it's very rare for it to take more than 5 minutes, as long as it's not, the database hasn't been overworked. But there are situations where someone's running a database on their own computer with like not kind of like too much specs, and that could take a lot longer, especially if they haven't got indexes set up. So it's really how you've configured your database and the hardware you have, whether it scales well or not. But most of the time when I'm doing it, the generation is not too long. It's the creation of it that takes me the longest. So if you're running a network study, you can get more information. The tutorial later on this afternoon will actually give you a full description of running a network study. But the process I use when I'm doing a network study is to first, you need to create that protocol. What is it you're actually trying to answer? What are you actually going to do? I've put 1 to 3 kind of like iteratively, because you may actually want to use the protocol generator where you actually need to design a study first. And it can be a rough study where you can then generate a protocol. And then for your protocol, you need to know what cohorts, and you can start generating some cohorts. Often it's good to use the community, though, to share the protocol and share the cohorts that you've got preliminary to see if there's feedback. And then you may iterate and actually do some more changes to your specification, to your cohorts, and that will give you a new final protocol. So this is iterative because it's good to get the community's input. Especially if you're someone like me, I know the tools and the software. I'm not a medical person, so I'm going to want to get input from a medical person on the clinical question and also the cohorts that have been generated. But once you've got everything specified, you can use Strategist and Atlas and Protocol Generator for those first 3 steps. The next step is advertising your study. How do you advertise your study? The way I tend to approach this is, 1, I post on the OHDSI forums. I try and get a 5 to 10 minute slot in the Tuesday OHDSI call to advertise it. And I also email people directly. So I see what studies have been done, who's done the studies before. I'll email them and say, hey, we've got a study. Would you be interested in participating? You do want to set a deadline, because if you don't set up a deadline for people joining and executing, I can guarantee 2 months down the line, after you've pretty much finished, someone's going to be like, hey, can I run this study? And you haven't put a deadline, and then you've got to tell them, no, sorry, it's passed. So I would put a deadline. It also is good to have that deadline to push people a little bit to run the studies on time. And then you want to actually to execute it. Once you've advertised and you've got people who are going to participate, again, you can use Strategist for that. So Strategist makes it, as you saw, it was just a very simple few lines of code to actually execute once they know their connection to their database. And then finally, the exploring. You're going to, if you're doing a network study with all of the different analyses, you're going to have a lot of results. You want to use the Shiny App Builder and OHDSI Shiny modules to actually explore those results and actually gain some insights that will help you with a paper. So these are the rough steps that I follow when I'm doing a network study. If you have want to know more about Atlas Hades and how to install Hades, I've got some further reading here. Again, you're going to get these slides, so these links will be available later today. And at that, I think it's a good transition over to Danny, who's actually going to be showing you some of the results of a network study.
Okay. Thank you, Jenna. I feel always when I'm talking about clinical applications of large-scale data like this, like I am, the lucky person who gets to show all the results after everybody has done all the work, and that is kind of the reality of it. I'm wondering whether anyone in the room has a clinical background or a pharmacy background or an epi background and is in a similar position to mine of basically designing a study, letting other people do all the work, and then getting the results and writing a report. Is there anyone in the room who is in that position? Can you maybe stand up? It's going to be good for your cardiovascular health if you do that, believe me. Anyone with a clinical background or an EP background or a pharmacy background in the room? Can you stand up, please? Okay. Yeah. So my passion no, stand up, stay standing up. If you're a clinician, you know that's good for you actually. Yeah, so my passion when I get involved in OHDSI and in all the OHDSI activities and studies is to see how data can actually make an impact on people's health. The condition we're going to be discussing is probably of interest to everyone in the room, definitely to the clinicians and pharmacists and people who are already standing up. But I wonder if anybody else in the room has been ever diagnosed or affected by hypertension, either through a relative, through a friend. Can you maybe stand up if you've been in either of those positions, and you don't need to say which will probably create a little bit of a legal problem. If you've been ever diagnosed or know someone who has been diagnosed with hypertension or affected by hypertension. Are people asleep, lazy, or lying? Hypertension has a prevalence of 40% of the population over the age of 50, so I cannot believe that only 10% of the room is affected. Okay. Anyway, this is probably the most common condition that we manage in medicine. I am trained as a clinician initially. I trained in Spain, trained in what we call the family practice. I don't know how you call it here. In the UK, we call it general practice. So we basically are the kind of first kind of gatekeepers to the healthcare system. And we are typically the ones that diagnose and treat hypertension initially. So this study is really, really close to my heart. What you see here in this slide is in this plot is the each of the individual therapies to treat hypertension available in the market at the time we did the study, and then each of the lines shows randomized controlled trial evidence, or what we would call typically gold standard evidence, comparing two medicines. What you have to the right is then the evidence produced by Legend, which is basically, as you can see, comparisons between therapies one-to-one for many or most of those treatments. Now, I remember very well when I read the paper by Mark Suchat et al. In The Lancet, which is the most clinically oriented paper that was published from Legend, finding it really interesting. And then very recently, after reading this editorial written by some colleagues who work literally across the road from mine in Oxford. This is an editorial where they basically talk about the magic of randomization versus the myth of real-world evidence, and how real-world evidence is just a new word for observational research. I'm going to try and respond to that in the next few slides. I have never done that in person to the people who wrote that thing. Not because I don't want to, but because we have never coincided in the same room. In any case, I think I'm going to start by saying that real-world evidence is much more than causal inference. So we do a lot of studies looking at the safety of products and looking at the effectiveness potentially of vaccines or medicines, for example. But there is a lot more than that that's needed to make decisions in the clinical world, but also in, for example, regulatory fields or in the HTA or payer decision making. You've seen this slide before. We basically typically classify this real-world evidence into these three buckets. One is characterization, the second one is prediction, and the third one is estimation. And the only thing I've added to the slides is the bit at the bottom, which is totally my opinion and my experience. So characterization is typically easy, prediction is hard, and population level effect estimation or causal estimation from observational data is the hardest. But I still want to show you that clinical characterization and prediction can really make a difference. Some of you will have heard of this Darwin EU initiative. Darwin EU is kind of similar to the Sentinel in the US, where the European Medicines Agency, the regulator for the EU, has funded this initiative for 5 years initially. And they have this ambition to generate hundreds of studies to inform regulatory decision making. Until now, and we are now at the end of year 3, I would claim that 90% of the studies we have done are characterization. So basically describing populations, describing treatments, looking at what people are taking, for how long, what doses, what route, and that is what we will cover in the tutorial on Darwin EU. We'll do this afternoon. What I really wanted to show you here is that if you look at the what we call the Darwin EU catalog of standard data analytics, where we say these are the kind of studies that we do all the time and repeatedly, most of them to the left are all characterization studies. And we do characterizations of cohorts of people, we look at the incidence and the prevalence of disease, we look at how treatments are being used, and so on and so forth. And if you're wondering why does a regulator want that kind of data, these are some examples of studies that we have done. So for example, population-level disease epidemiology, things as easy as looking at calculating incidence rates in a cohort or in a whole population, or looking at the prevalence of a condition, are extremely important for regulators because they will need to make decisions on whether a condition is rare enough to warrant a kind of speedy approval process that we call orphan medicines approval in Europe. So prevalence of rare disease, kind of study we do very, very often. Background rates of adverse events of special interest. I don't know if people in the room are exposed or have been exposed to pharmacovigilance practices, but typically when a new product is in the market, you need to know what are the expected side effects that could happen, and you need to have a background rate in the population that will be exposed to the product, so that if you then accumulate lots of reports, spontaneous reports from people saying, look, I had this vaccine or this medicine, and then immediately after I had, I don't know, arrhythmia, then you can compare whether that adds up to a number higher than what you expected. And what you expected is what we get from these background rates. So again, another very common type of study. Patient-level disease epidemiology, this is when we get a cohort of people, typically with a condition. It could also be that they are characterized by taking a specific treatment, and we will want to know what is the natural history of that condition and what is current practice or treatment, or what are the treatments being used for that disease. That is, again, super important because sometimes there will be applications for new medicines where the marketing holder or the company producing that therapy might want to claim that there is no treatment for that condition already, and you want to see what's happening actually to those people in the real world right now. And then finally, drug utilization studies, a very interesting type of research where we are interested to know whether a medicine is increasing or decreasing in use over time, and we want to know also what are the indications for that treatment, how long are people taking it for, at what strength, what is the cumulative use, and so on and so forth. Okay, I'm going to jump straight into what we would call population-level effect estimation or causal estimation, unless there is any question on characterization studies. My colleagues have already shown you a few examples of these kind of studies, and I will still show you some stuff. Okay, so safety. This is a study that I want to highlight just to tell you that if you are wondering what is the impact of large-scale evidence on the real world, this is a study we did in the middle of COVID. Some of you might remember this because we were working together remotely for like a few days, and we came up with this analysis where we were comparing the risks, cardiovascular risks associated with the use of hydroxychloroquine and with hydroxychloroquine combined with azithromycin. It might sound like old news now, but at the time, something like 50% of people in some countries in the world were taking that combination of two treatments. And this research led to a regulatory advice and to a regulatory letter by the European Medicines Agency, as you can see on the right. And if you're wondering what was the impact in the real world, and if you're wondering, how did this compare to trials? And again, I don't want to say that trials are not necessary. I don't want to claim that trials are no longer needed. I just want to say there are situations where you will want to learn from the data that you already have available to you before you can wait for the trial. So this is the proportion of people admitted to hospital in different parts of the world that were being treated with hydroxychloroquine during 2020. You see how in February that was variable, but still relatively low. In March, there was an emergency authorization approval, and that increased in March and April. In April, we pre-printed the paper that you saw, showing that there was some risks, and there were other colleagues around the world showing similar results. And there were these two warnings by the FDA and the EMA. And in May and June, you can see how there is hardly any more people taking hydroxychloroquine when they're admitted to hospital. I just want to tell you that my colleagues also, the same people who wrote that editorial, the colleagues across the road from the big clinical trials unit in Oxford, were running the recovery trial that you might still remember, which published a press release in early June saying that hydroxychloroquine was actually not effective against COVID-19. So we managed to make an impact on the use of that treatment based on safety grounds and real-world evidence well before the trial reported also a lack of efficacy. Okay, so back to legend now. I don't know if people have ever, particularly people who are clinicians or pharmacists are interested in this, but also I guess anyone who is doing research in this space, you should be interested to know why you're doing the research that you're doing. Reading or participating in any of these guidelines is quite an interesting exercise. I have participated in rheumatoid arthritis guidelines because after being a GP, I went to the UK and trained as a rheumatologist. There's a lot of pages that go into a guideline like this. There's a lot of evidence that gets summarized, but there's also a lot of opinion that goes into these guidelines, basically when you don't have evidence for a comparison. So in this particular clinical practice guideline of the American Society of Hypertension and loads of associated colleges and scientific organizations, there were 56 pages and 106 recommendations. If you look specifically at one of those recommendations that I think is very important, you can see how, if you look at oral antihypertensive drugs for first-line therapy, so this is somebody has been just diagnosed with hypertension, you need to give them a treatment, what is the best treatment you should offer? And I don't know if the clinicians in the room want to take a guess on what you would do. I can tell you, when I was treating hypertension in 2009, I guess, 15 years ago, we would go for, at least in Spain, hydrochlorothiazide, so a diuretic, or an ACE inhibitor like lisinopril. In this guideline, when they talk about the thiazides or the diuretics, they say clotharidone is preferred. And I remember at the time there was a little bit of a discrepancy between the American and the European recommendations. The American guidelines recommending clotharidone over hydrochlorothiazide. So in any case, there is right there, a comparison somebody could do, and we really needed data to say which one is better of those two treatments. There was at the time a large randomized control trial going on precisely trying to answer this question. As you can see here, this trial was comparing diuretics, and what we did in Legend is, as part of the whole Legend project, compare these two treatments. So there was a comparison between clotharidone and hydrochlorothiazides, and you can see here the whole detail on the study design, but what I'll cover very briefly is the outcomes, including efficacy, which was prevention of cardiovascular events, but also safety, and particularly there was, at least at the time, a concern that diuretics could lead to the loss of ions, and you could have hyperkalemia, hypokalemia, and problems like that, and potentially renal problems. So the trial started in June 2016, wanted to enroll 13,500 patients, and it was due to finish in October 2022. And we wanted to see what could we learn from this large-scale real-world evidence study run by OHDSI while we were waiting for the trial results. This is a paper led by George Ripsack that you'll find in JAMA Internal Medicine, reporting the results from the Legend study, comparing cardiovascular and safety outcomes, cardiovascular being a measure of effectiveness because you are trying to prevent cardiovascular events in people with hypertension, and safety outcomes of clotharidone versus hydrochlorothiazides to treat hypertension as a first-line therapy. And these are the results from the Legend study, where you will see there is no real difference in cardiovascular outcomes. So you can see how the overall calibrated hazard ratio includes the null and is very close to the 1. So probably no difference in cardiovascular events between both treatments. If you then look at safety, you can see here, although it's very small, that there is an increased risk of hypokalemia with clotharidone compared to hydrochlorothiazides. These are the diagnostics that Linjing covered earlier, where you can see how there was some equipoise. People will remember this. That, of course, improves after you do propensity score adjustment. I think this was matching. And then you can also see the plot that she showed you before for all the baseline characteristics of the patients taking one or the other treatment before matching and after matching, and how that reduced the observed confounding quite dramatically. And then to the right, you see all the outcomes And to the bottom, you see the forest plots with the results from different databases and a summary estimate that you have seen already. So no difference in effectiveness, and as I was saying, potentially a higher risk of hypokalemia with chlorthalidone. Now, after this paper was published, there was an editorial that followed, where again we go back to the mantra that observational data cannot produce causal inference. And there is this mention there that there is a substantial likelihood that residual confounding accounts for the lack of an observed difference in cardiovascular endpoints in the paper. For this reason, it is imperative that we need to do the trial and wait for the results of the trial. If you read the whole editorial, we go back to the whole idea that we do believe, that chlorthalidone is better, which is kind of interesting, right? When you're saying this super large study with I don't know how many million people is not really very good, but my opinion is brilliant. So let's stick to what we are doing already while we wait for the trial. Now, I want to have a show of hands to say to vote and tell me whether you think that the trial showed the same results for effectiveness first, the same results as the LEGEND study, and then we'll do the same for safety. Who thinks that the trial, when completed, and don't cheat and look at the next slides, who thinks the trial, when completed, showed the same results as LEGEND for effectiveness? So that would be no difference in cardiovascular outcomes. Hands up if you think it showed the same. Okay, hands down. Hands up if you think they showed different results. The trial showed different results. There was one hand there that was very shy and went down very quickly. Do you want to say why? What do you think that it would be different? She doesn't want to say it. Okay, she'll say it to me over coffee later. Okay, now safety. I think safety is the most accepted application of real-world evidence, right? So, but anyways, who here thinks that the results from the trial would be essentially similar to those from LEGEND in terms of safeties, including the increased risk of hypokalemia with chlorthalidone? Hands up. Hands down. Who thinks they were different? Hands up. Can somebody who thinks they were different tell us why? Yeah, there's a hand there. Okay, so what the colleague there is saying for the recording is that he thinks that potentially there could be a difference between both studies because the trial should be smaller and shorter in follow-up, I guess. I think the effect side we were looking at here, hypokalemia, tends to happen early after you take the treatment, so not necessarily a difference in terms of follow-up. In terms of sample size, this trial was relatively large. It was 13.5 thousand people. So although those two concerns or issues are very common, I wouldn't think they should be very important here. Yeah. Any other reasons why somebody else thinks that they expect different results from the trial versus the study, the LEGEND study? No? Okay. Let's see the results. So this is the trial published in the New England Journal of Medicine. You can see there how, the magic of randomization has worked again, and you get comparable groups, as you would expect, of course. And then when you look at the outcomes, you can see how the overall hazard ratio for the primary composite outcome, which is cardiovascular disease, is 1.04 with a hazard ratio crossing the null, so very much similar to what we saw in LEGEND. And then if you look at each individual cardiovascular event, there isn't really anything that stands out. So there is very, very much a similar rate of cardiovascular events. So in terms of effectiveness, chlorthalidone and hydrochlorothiazide would be equivalent. Yeah. If you now look at the side effects, there is in here, it's very small, but you can see how hypokalemia, which is this reduction in potassium levels, by the way, for people who are not clinically trained, in your blood, hypokalemia is more common with chlorthalidone compared to hydrochlorothiazide. So again, very much similar to what we had seen in LEGEND. Yeah. Here you have the comparison between both. Cardiovascular events in Legend has a ratio of 1.00. The trial shows 1.04, both with the null included in the confidence interval. Hospitalization for acute MI, similar. Hospitalization for a stroke, similar. Hospitalization for heart failure, similar. And then hypokalemia. I would say they are potentially different in that we see more hypokalemia or more of a difference in the Legend study, but the difference stays there in the trial as well, right? So they are consistent, but different in terms of magnitude. Now, this could just be a lucky shot. It could be that we just got lucky and we happened to nail it with that one. And what the colleagues did, and this was presented by Patrick in the OHDSI Symposium a couple of years ago, was compare how similar are the trials to each other when a trial has been repeated more than once. So when the same comparison has been done more than once, how similar are those two trials? And then do the same comparing the trials to the Legend study, yeah? So you see here the 15 randomized control trial replications on the same class-class comparison. So this is where, you know, for example, you have for atenolol, you have two different studies or more, same would be atenolol versus lisinopril. Then you have, so for each drug pair, you have more than two or more trials doing the same thing. And you can see here how, I guess as one could expect, the trials look kind of similar, like these two look potentially similar, but not entirely. Like, for example, this one, if you look at the confidence interval, wouldn't show a difference in whatever that outcome is, but this one would, right? And the same would be true there. So trials are not infallible either. Like, you do have sometimes a trial that gives you an answer, and then you repeat the trial and you get a different answer, yeah? But overall, you could say there is quite a lot of concordance between trials. There's a lot of ways you can measure concordance between two studies. You can look at whether they give you the same result in terms of the estimate. You can look at whether the confidence intervals overlap. You can look at whether the decision you would make from the trial would be similar. So, for example, if you see an increased risk in one but not in the other, that could potentially lead to different decision making. But overall, you see the metrics here of the comparisons of those 15 trials. Now, if you then look at how many of the Legend analysis could be compared to trials, there's a total of 31 RCTs that can be directly compared to Legend in terms of the drug-drug and outcome comparisons, yeah? And again, similar to what you saw before, some of them quite consistent. Typically, of course, the Legend ones will be more narrow than the trial data because of a number of patients or power difference. But overall, kind of similar and not that different, right? So maybe that mantra that you cannot really get causal inference data from observational data sets is not really true. If you, in fact, compare the metrics of concordance between RCTs that have been performed and the Legend study, they actually look very similar to the trial comparisons. Yeah? So you could say, in a way, in response to that editorial, that trials replicate trials as much as real-world evidence using best methods and best data replicate trials. Okay, now I'm going to make you work. I think maybe Erica can write in the chat this same link so people can click on it quickly. This is going to be a real test because I don't think we've ever had a room with over 100 people trying to hit a Shiny app. But what I'm going to ask you is that you open this Shiny app that you have here. Maybe you can do it 1 or 2 computers per table. You don't need like individual computers. Like you don't need 5 or 6 or 7 computers per table to do this. And I'm going to ask you to connect to the Shiny app, and I'm going to let you do some work and look at the comparison of interest, which is amlodipine. This is a calcium channel blocker compared to lisinopril, an ACE inhibitor, and the outcome of interest here is going to be cardiac arrhythmia. You will see that the Legend study did loads of different analyses, and I want you to focus only on the propensity score matching, where we match people taking both treatments and try to compare them. And then you will see also that there's a number of options, and I want you to focus on the on-treatment option. Yeah. So just to show you what this should look like, you should get something similar to this. You should get indication hypertension. You should compare the drug or procedure amlodipine as a target, lisinopril as a comparator, outcome cardiac arrhythmia. You then have in there a number of data sources that were analyzed for this. And if you scroll down, which you cannot see here, you would then get to choose the propensity score matching and the on-treatment analysis. I'm going to try and go to the... Are there any questions? Are people managing to connect to this Shiny app? Sure. So in the meantime, I will show you in mine, hoping that I have some sort of magic right that makes me be able to go faster than you. So basically, you need to compare amlodipine to lisinopril, which is going to be here. And then you're going to look at the outcome of cardiac arrhythmia. I've shared a different Shiny app with you so that at least I can get to run mine. Is it working for you guys? Is everybody connected? Are you managing to see this or something similar to this? At least one person per table? Any table that cannot connect to this thing or cannot make anything work? Okay, otherwise, assuming that you are connected, if you are not raising a hand, I'm assuming you're fine. Please choose one of these data sources. What you have here is the results from each of the data sources, yeah? And then you have the meta-analytic results. Don't go for the meta-analytic results. Go for one of the data sources. And then when you click on it, you will, wait, stay with me, please. Then you get all these things at the bottom, yeah? And you will get this is the real test on what Linjing was showing you earlier. So now you get to see these yourselves. And per database, I want you to take a note on whether your analysis passes the diagnostics that she mentioned. So one is power. If you click on a database like CCAE in this case, don't use CCAE, by the way, because this is the one that I'm going to be using. If you click on CCAE, you see power. You got an MDRR that's very low, 1.06. Then you could see your propensity scores, and you would see the overlap or the equipoise, as she called it. You could then go to covariate balance and then see this large-scale characterization where you expect that all the dots in the y-axis are below 0.1 threshold, and then you would get your systematic error here, yeah? Can I ask, for example, that people on the right-hand side of the room, those tables over there, please go for CUMC. The next row or column, I guess column for me, takes IMSG. The middle one takes MDCD. Next one, MDCR, and the left one takes Optum, please. Spend something like 10 to 15 minutes going through these diagnostics, and I will ask you what you learned. If anybody has a question, raise a hand, and I or somebody else will come. Basic parameters, you need to go to hypertension, drug or procedure, because you can go for drug classes as well. Amlodipine, lisinopril, cardiac arrhythmia, and then at the bottom, PS matching on treatment. Any questions, raise your hand, otherwise you have 15 minutes. Erica, how much do you want to leave? Any questions, raise your hand. I want multidisciplinary teams. So I want that each table makes the most of the people that you have in the table, yeah? I'm going to take a picture to share it with my colleagues later. If you have any concerns with that, raise a hand if you don't want to be in the picture. You have 5 minutes. 5 minutes, please. If you can choose someone from your table who can be the speaker for the table when I ask questions on diagnostics, please. One person per table, take a note on whether your database passed diagnostics for power, for equipoise, and for systematic error. Erica, is there anything in the chat? Questions or anything in the chat? Jenna is... I'm pretty sure it was. 30 seconds, 30 seconds. Please take a note of your conclusions. One person per table, please. Are we going to regroup? Okay, please take a seat. I need coffee more than you do. I arrived yesterday from Europe. I woke up at 4 a.m. today. Okay, I'm going to ask row by row about the diagnostics that we've looked at. So let's say for power, all the diagnostics, by the way, are quantitative, and then we somehow randomly put a threshold to them. So for power, for example, you could say, for this particular study, I'm interested in databases that have an MDRR below 2, because I think that the hazard ratio should be below 2, yeah? Can I ask people on the right-hand side of the room, people in that column over there, I think you were looking, what database was that? CUMC. Can you tell me, power-wise, how did the database do in the analysis? Maybe the first table on the right-hand side. What was the MDRR in CUMC? Was it below 2 or above 2? Below 2, so it would pass the diagnostic for power, yeah? If we said 2 is our threshold for power, we would pass the diagnostic for power. Did any other database not pass this diagnostic? Did any database have an MDRR above 2? Can you raise your hand if that was the case? Yeah? Which database? NDCR? What was the MDRR? Let's get you a microphone because I can't hear you.
Who's speaking? Sorry.
Sorry, the MDCR, the power calculation came up with an error.
Oh.
So I don't know if that is valid.
That's interesting. I didn't see that coming. MDCR showed in my screenshots an MDRR of 1.11. So maybe there was something when you were trying to run the app or something, but it would pass the diagnostic of power. Yeah. So basically, if you look at all the different data sets, the only one that got kind of close to 2 was IMSG, but all the other databases would pass diagnostics based on power. Okay. Now, the next diagnostic would be equipoise, which is basically the overlap between the different propensity scores when you're comparing these two treatments. Can I get somebody else from that same column to tell me, some other table, please, what was the overlap? Was it more than 50% or less than 50%? Raise a hand if you think it was more than 50% in the overlap. Very shy hands. Do I need to? I don't like shouting like Mui. I've been given a microphone. Did you see any instance where the two groups you think had less than 50% overlap? Can you raise a hand if that was the case in your database? I'm going to ask the counterfactual to that just to see if you're awake. Can you tell me if you think there is more than 50% overlap between both groups in your database? Hands up. Okay, they still have the room that's more asleep than I am. Okay, basically what you're expecting is that, and a colleague here asked a very good question, because you will see that in the app you can choose between matching and stratification. Matching is basically when we get that beautiful distribution of the two populations, and we look basically, summarizing, at the purple area where you have people who look the same or look very similar. Stratification would be where you take that distribution and break it into deciles, quintiles, whatever you want, and then you produce an estimate for each of the strata and pull them together. Yeah. So matching will only include the people that are in the common area of support, or people who look the same or very similar. The stratification would include everyone, and that's basically answering two different questions. Yes. So don't be surprised if sometimes you get a different question, a different answer. Okay. In any case, if I look at the databases, this is quite good actually. I think as we predicted, and we as clinicians, people in the room who are clinicians or pharmacists or who have some pharmacology training would know that you could expect that when you have to treat people with a diuretic for hypertension, the choice of diuretic is a bit, iffy at best, right? Like people will make decisions based on many reasons, not that much based on evidence. So you wouldn't expect to see very different populations. You would expect to see similar people, okay? The next diagnostic is covariate balance. There's a ton of simulation studies, plasma simulations, loads of studies have been done showing what is the best threshold in terms of differences between groups to produce reliable causal inference. And most of those studies suggest an SMD above 0.1 is undesirable. So you definitely want all your covariates to be below 0.1 in the y-axis. Can somebody maybe from the middle row, and not Jamie who knows more about this than I do, tell me if you saw any imbalance in any covariate above 0.1 after matching, after propensity score matching? That would be in your y-axis. Did you see any covariates crossing the 0.1 threshold? What about before the matching? Did you see differences between groups before matching? If you hover over the plot, can you see what covariates they are? I'm going to try something very brave and go back to the shiny. So I think the new versions of the shiny would be better at this, but I'm pretty sure that we did see this. Cardiac arrhythmia. Okay, so if I go, for example, CUMC, and I look at the covariate balance, I see this massive plot, right? The x-axis is before propensity score matching. Yeah, each dot is a covariate or a baseline characteristic, and if I hover over them, I think I see, for example, pure hypercholesterolemia was more prevalent in one group than the other with an SMD of 0.15. Yeah, so that was definitely something that, as a physician, if you tell me I'm comparing these two groups, one of them has a much higher prevalence of hypercholesterolemia than the other. If the outcome is cardiovascular disease, I would kind of worry that those are not comparable groups in terms of confounding. Yeah. So that's definitely something that we solved by doing propensity scores, because after the propensity score matching, you see the difference now is 0.04. So they are very much comparable, yeah, below 0.1, okay? And if you hover over this, you would see others, like, for example, use of antiseptics and disinfectants was somehow different. I wouldn't worry a lot about that, to be honest, but that's something that we also resolved in the matching. Abnormal metabolic state in diabetes mellitus, that would worry me, because diabetes can cause cardiovascular events, and so it goes, yeah? If you had anything above the 0.1 threshold, so anything in the y-axis above here, I would recommend having a look at what that is, because, sometimes you just get random variables that are not necessarily confounded, so you want to look at that. Okay, final diagnostic that Linjing discussed was, she called it EASE. We didn't have that metric at the time. But basically what you want to measure is, okay, now I've matched my two groups based on propensity scores. They look alike in terms of thousands of covariates, each of those dots in the plot that we just reviewed. Thousands of covariates now look similar. I don't have any evidence of confounding based on the data that has been collected. But still, people who don't believe in observational data would tell you, well, yeah, but you maybe have something that you haven't collected that is still different, yeah? If that was the case, you would see evidence of systematic error. So you would see that the risk of having negative control outcomes is imbalanced across groups, yeah? Did anyone worry that you saw evidence of systematic error, so that the groups had more or less associations with the negative control outcomes than you expected? Can you raise a hand? There's a colleague over there. Anybody else? Everybody else was happy? Were you happy or asleep? Or happy asleep? Can we get the microphone over there? And I think this will be the last thing I will do before I pass it back to Erica.
So in Optum, not all of them kind of matched our 95% threshold. They're all very close, but if we're going for a really strict 95%, or if, like most recommendations, we can be a bit subjective. I think they're pretty close, but depends how strict we're being with them.
Yeah. So this is a tough call, right? It's a little bit, what is really the threshold that you want to put in there? I mean, chance is, like you could say, there's more than what you would expect based on chance, but there's also a component of power, because you could say, if you have very rare negative control outcomes or a very small database, you would potentially never see associations because you just don't have power to see them, you know? So there's that kind of both things in the equation, which is why the ease metric is probably preferable. I would say that, for example, in this example here at the bottom right of my screen, I do see something that worries me, in that all the negative control outcomes that are beyond the dashed line, which is the 0.05 threshold, are to the right. So there's like some evidence that there's maybe some systematic error there, yeah? Whilst others are not so much like that. Like the ones at the top, for example, the top row I think is fine. The bottom row maybe is fine, but the two to the right of the plots look a little bit dodgy to me, yeah? They look like there is clearly an imbalance, that the negative control outcomes associated with the treatment are to the right-hand side of the null, yeah? So that would mean that you are kind of overestimating risks in a way. So that needs to be accounted for using calibration. Okay, well, I hope that was fun. I'm going to pass it back to Erica to wrap it up. And thank you, everyone.
Okay, so since you're seeing me again, that means we're getting to the end here. And first I want to acknowledge we went through a lot of content very fast. We don't typically go through this content. Like if you're actually trying to digest the content, we have like lectures that are like 8 hours for the CDM and 8 hours for methods research. So if you felt like there were parts of this that you just did not get, that's totally fine and totally appropriate. But what I'm going to talk to you about now is, if you are interested in learning more and getting more involved, how can you become a member of the community? Okay, so our community, the OHDSI community, is always seeking new members. And like I said, you might be really passionate about data and data standards, and maybe what Danny just talked about is less of an interest for you. That's completely fine. Or maybe you're a clinician, you just want to ask clinical questions. That's also fine as well. Again, we're a community of folks coming together, and all our skills together allow us to generate evidence at scale. So there's many ways to participate. You don't need to know everything that you heard about today in order to do that. So I'm going to talk through kind of like the standard things we tell people if they'd like to get started. So on our odyssey.org website, you'll see that there's always a menu item that says New to OHDSI. And under New to OHDSI, there's tools and discussion about like what you would need to join. But I'm going to point out a couple things that are pretty important. So first thing that I would do if I were joining OHDSI is I would join the OHDSI forums. And this gives you a way to connect with members of the community. And I've actually talked to a few of you today about the forums themselves. So for example, like I said, we threw a lot at you during this discussion. There's no way that you were able to consume all of this. If you have questions, the OHDSI forum is a great place to ask those questions. So for example, in preparing for this presentation, I went out to the forums to find an example, and I just happened to stumble upon somebody asking a question recently that said, hey, I have a CDM and I've run Atlas, but I'm not really seeing the drug error reports. And so when I saw this question, I was like, oh, I might know the answer. So I was able to reply and say, hey, I think maybe you haven't actually built your drug era and condition era tables yet, and here's a link to find more information. However, if it ends up being maybe there's something wrong with your tool and it's not implemented right, I then was able to tag a friend like Frank DeFalco and say, hey, Frank, maybe you can provide some more information if that's what it is. So I would say on the forums, no question is, too simple. This is a great place to ask things. So the second thing that I would do if I was joining the OHDSI community is I would join the OHDSI MS Teams. This provides us a place to collaborate. So first, we do have weekly meetings within OHDSI, and we do use an MS Teams tenant in order to facilitate those calls. You do not need to be on the MS Teams tenant in order to participate in the calls, but it sometimes gives you a little bit more features to interact on the calls. But if you were to join a working group, the MS Teams environment provides us a place to collaborate. So for example, if your team is discussing something and you have a Word document that everybody's working on, the Teams environment provides you a place to not only interact on that document, but also chat back and forth about things that are going on. So for example, I have a screenshot of the OHDSI working group team site. This is a very busy team site, and earlier in the year we had what we called the April Olympians, and we challenged the community to help participate in updating documentation around the CDM. And so while we would go to the community calls and talk about it, people who were actually participating would come to the team site and talk back and forth. So you can see here, Claire is talking about this week, we're going to do X, Y, and Z, and people were allowed to talk and say, hey, I did my thing, or I did this. Another thing that I would do if I was joining OHDSI is I would join the community calls or work group calls. So like I said, we do have for the global group, we do have a weekly call. It's on Tuesdays, 11 a.m. Eastern Standard Time. Totally recognize that that date and time is not great for everybody. I do believe, Mui, there is, like, for example, an Asia Pac chapter call that's at a more appropriate time, right? Yeah, so there are other calls that happen that are more general OHDSI type calls. And then 11 p.m. works for some people and doesn't work for other people. But then there are also work group calls, and so it's communicated fairly often, okay, in the next couple weeks, here are the different work calls, and here are the dates and times that you can attend those. So joining the calls are a great way to see what's going on in the community. In the community calls, I would say periodically there are newcomer calls, and those are great ways if you're like waiting for a good entry point. You don't have to, but we have those periodically. Also, if maybe joining a call makes you nervous and you don't know what you're walking into, all the calls are recorded, so you could go and view one on YouTube and see what it's all about. You can also just consume it that way. So again, for some of our friends in Asia Pac, that's how they're consuming the call, is by watching it when it gets released on YouTube later in the day. There are other ways to learn about OHDSI. So we have something called the Book of OHDSI. I think about 5 years ago now, we set to document actually a lot of the content that we walk through today. And so if you're like me and you really want something to kind of read through on your own time, the Book of OHDSI will go into a lot more detail. It's also a wonderful resource if you need to like cite or say like, hey, like this is how OHDSI is doing it. There is a book. The book is freely available online in a like PDF format, like it's nicer than a PDF, but like you can navigate through it. But if you do like a tangible book, it is available on Amazon. I know I kind of like to hold the book in my hands. This is not a sales pitch. It's like literally at cost, so you can order it and then have the physical book as well. And it's translated into a bunch of different languages. I know Korean and Chinese are done, but I know Martine's been working on French, so there are different versions depending on your needs. We've mentioned a couple times today that there are tutorials, like 8-hour tutorials that will go into more detail. And when Eden first started, this is an IMI project that happened in Europe, they realized that as they were bringing people onto the project, they needed to have a way to train people on what was going on. And so they generated something called the Eden Academy. Eden Academy is freely available to anybody who wants to go and see learning materials. You do have to create an account, but there's no barrier to entry other than that. And these like 8-hour lectures that we keep referring to are all recorded and available in the Academy. So that's a great way, like if you want to get more in depth on CDM and the vocabularies, we have those tutorials recorded there. And then last but not least, we have pretty much everything we do gets recorded and put on YouTube. So there's very often where I need to see something or see somebody talk about something, and I'll just Google like cohort diagnostics tutorial, and then a 10-minute conversation of Gauth and Rao talking through cohort diagnostics will come up. So YouTube is a wonderful resource to learn more about what's going on in the community. Those 4 steps are kind of the main ways people will tell you about joining the community. And I want to just highlight a few more things for you guys. So I believe Jenna actually touched on this, or Lin Ying's touched on this a little bit. We have a OHDSI Studies site. So if you wanted to see different research projects that are going on in the community, this site actually scrapes GitHub and looks at the different studies that are going on, and will say like, okay, I can see that this last repo was updated 5 days ago. Here's the main person working on it. Here's the title. Here's the protocol of the study. So if you are interested in clinical questions and you're wondering what some of the questions that the community is asking, you could go out here and learn to see, oh, I can see Chen Yanover is working on an IBD study. That's an area of interest to me. I could either connect with Chen and learn a little bit more, or I could even just grab his code and see, can I even run his study in my environment? You don't have to share it back to him. You could just run it and see, can I even execute an OHDSI study? So I think this site is a great resource to kind of see what's going on. Another thing that I probably you'll hear a little bit more about tomorrow is the OHDSI Evidence Network. So one of the things OHDSI is trying to do is get a better handle on who in the community actually has CDMs that are potentially available for research. Back about 10 years ago, when our community was small, it was really easy to know which groups had data and who was interested in doing research. But we're now at the size where people have CDMs and we're just not even aware. And so we are trying to create an evidence network, which is essentially a list of databases that are converted to the OMOP CDM. And the idea and the goal is to connect people who have study questions to data sets. But we also recognize that just because you have a CDM doesn't mean you're in a position to participate in network research or even have the desire to. So the OHDSI Coordinating Center is kind of like the go-between. So if, let's say I have a study question, I can work with the coordinating center to say, hey, I have a study question on type 2 diabetes. Are there any CDMs in the network that would be able to run a study about type 2 diabetes? The coordinating center will say, hey, yeah, I see that there are 20 data sets that could run this study. We will help bridge a connection between the two of you, but still at the end of the day, it's up to the data partner whether they want to participate or not. But we are just trying to make sure people are aware of what is out there. You see a QR code on there. This is if you are interested in learning more about the OHDSI Evidence Network, or if you have a data set that you want to make sure that is part of the OHDSI Data Network. This is an active initiative that we're working on now and building out. Okay, and last but not least, I know this was a ton of information and it's really hard to kind of digest it all. So tomorrow during the plenary, if you guys are here and things are being talked about during the plenary that you're just not understanding or you want to learn a little bit more about, we are going to have essentially a help desk. So during the poster session, I think the posters are like downstairs. Outside, before you go down the stairs, there'll be a desk and one or more of us will be there. So if something was said during the plenary and you just don't understand, please feel free to come over to us and ask us questions. If you see us in the hall, please feel free to just stop us. We recognize that this is a lot. So with that, I'm going to ask my faculty friends to come up here and maybe bring that mic up here as well. And we're going to open it up to a few minutes of questions and answers. And as the faculty is coming up here, I'm going to just say two administrative things. First, for those of you who are interested in having certificates of completion of this course, they will be sent to you via email after. And then also there are other tutorials that are going to be happening here after this session, so you need to take your materials with you because they're going to, I think, dividing the room and bringing others in here. So with that, we have time for discussion. Does anybody want to ask any questions? Jenna, come up here. Jenna Raps. Oh. Might not be on.
How about now? I really like the diagnostics. And so in the VA, we're trying to do more of the diagnostics piece. I guess since I've learned this several times, it takes a minute to sink into my thick head. But the EASE score is completely dependent on negative controls. Is that what I learned today?
I think that's what I said today. And I think I'm right with 99.9% confidence. And I like that you love diagnostics. I think, yeah, we all love diagnostics, but especially when a study passes all those diagnostics.
Yes, it's good when you pass, for sure. So if the EASE score is always dependent on negative controls, what's the state of the art in terms of when you're creating an OHDSI network study, how do you start with the negative controls, and who and how do you whittle down to get the right ones for your particular study? Would that be all right?
The question is about how we choose negative controls for a specific study. That's a great question. Actually, I got that question during the break from researchers in our audience. So the negative control outcomes are curated set based on parsing through a lot of the PubMed medical literature that existing out there. So we're looking for evidence of drug and outcome pairs that were found to have no significant effect. So actually in Atlas, you can put in your target and competitors of interest, and that will, and you click a button that will generate a list of negative control outcomes from the algorithm. And then we typically filter based on frequency of those negative control outcomes in your study cohort, because when the negative control outcome if it's too rare, then it's very unstable to make predict estimations, build models on rare negative control outcomes. And typically we, after you do the frequency filtering, then we do manually review with clinicians, clinical clinicians or domain experts to ensure that there isn't any doubts or questions about the validity of those negative control outcomes. And we typically shoot for somewhere between 50 to 100. And that number is not fixed because sometimes there's fewer negative control outcomes that we can select for a particular study. But I think overall, yeah, we need to do more to really make the negative control outcome selection and the pipeline more precise and concrete.
One question, this is sort of a statistical question, if you have some expertise on that. So as we were looking through the application, I was surprised to see just how many T's and C's there were. You could pick like a number of, any one of many T's, one of many C's. A question came up about when looking at like the statistical results and stuff, is there some multiple testing consideration, adjustment that needs to go into these statistics, or are they considered completely independent like calculations that don't have anything like that?
That's a great question. I think it's certainly a concern, multiple hypothesis testing. If we're doing many treatments, many outcomes, we're doing many hypotheses. Yeah, I'm not sure. I'm not sure if we currently have existing pipelines to handle multiple hypothesis testing, or if anyone have looked into that from a methods perspective. But I do see your point. I think it's a valid.
I'm just wondering. I don't know. Like, so it's not like we looked at all the whole list sorted by significance, therefore sort of doing a cross comparison across all these results, and like that would be the multiple test versus somebody just opening up random ones over and over and over until they finally find the one that was statistically significant. But we have so much diagnostic that goes into these analyses as far as propensity score matching and understanding systemic error and stuff like that. I don't know if that overcomes the notion of, like, you can trust that this statistically significant result actually is based on a balanced population, all this other stuff. So I don't know either. I was just wondering if you guys had any background that maybe I'll shop around that question and see if somebody has some other insight on that too. But thank you for trying there.
Yeah, thank you. I'm happy to work on a project on that topic.
Indeed, thank you. I'm passing it along, so now you have to do it next.
Thank you. Yeah, my question is around diagnostics. So I wanted to ask how strict these diagnostics are. For instance, let's say if a couple of variables fail on SMD kind of diagnostic, do you just stop there, or do you still do your analysis, and yeah, what is the action after that?
Actually, this is probably Jamie Weaver can speak to this better than I can. But to quote Jamie Weaver, I would say typically with the diagnostics, there are no hard limits that each one you would say like this is a pass or fail. However, what we typically say is like you want to predefine them before you actually run the analysis. So if you have a certain diagnostic, you say, okay, this is going to be my cut point for a yay or a nay. And then if the diagnostic says you should not look at this result, then you have to adhere to what you pre-specified up front. Jamie, did I do an okay job? Okay.
Yeah, thank you. That's a good strategy. Thank you.
Hi, Chris Villon, McGill University. Thanks for a great session. I guess my question is also about diagnosis, particularly the ease statistic. And I guess I'll give the disclaimer of I'm one of those epidemiologists Danny was trying to get stand up for. What bias are we trying to assess with the ease statistic, or is it just a accumulation of bias?
I think the wording we've used in this session is systematic error, right? So that would be after you have done your best to minimize confounding, do you still have systematic differences across groups, which in our usual kind of jargon you would call residual confounding. So basically you've done all your efforts, propensity score matching, what have you. You reach comparable groups in terms of everything observable in the data, but then you still have this, wonder or this worry that maybe there are differences that are still systematic across both groups, and that's what you measure with these diagnostic.
Because I guess, you guys have clearly thought about this far more than I have. Because I guess I'm wondering, when we select one negative control, we often try and pick a negative control for which, we expect a null result, but that would mimic the confounding structure of the comparison that we're doing. Here, when you have 50 or 100 negative controls, it's hard to mimic that confounding structure across that many that many outcomes. But I also wonder if it also picks up issues such as detection bias, which would be a measurement or an information bias rather than confounding. Like the example that was used about the ingrown toenail. Well, I could easily picture someone going to see their physician, and while there, just like the numbers of skin cancer diagnoses that are in part just due to differences in detection. So I'm I guess wondering if there's any plans to try and delve into that a little bit further to assess what the different components of bias that could be at play.
Yeah, so I think when we teach or learn classic epi, we are taught indeed that your negative control outcomes, the ideal negative control outcomes are these outcomes that are not associated with your treatment but share the kind of causal and structure, right? So you would spend hours drawing DAGs in the whiteboard until you come to the conclusion magically that you're happy with your negative control outcome. You say that cannot be done for 50, but it can be done. I've done it. So when Linjing was telling you the different steps that we follow to create a list of negative control outcomes, you could embed in there a step that says, I'm going to review all the negative control outcomes one by one. And reviewing 50 negative control outcomes is work, but we said already that we are the ones that get all the credit at the end, right? So we might as well do a little bit of work. So I do that sometimes. I also agree with you, though, that kind of classic view of epidemiology is not always that useful in real-world evidence, because sometimes you want to learn about systematic error that has to do with things that are not necessarily causal, but have to do more, as you were saying, with detection bias. Like, do people who get this treatment that's perceived as, more dodgy or more expensive, or, do they get more measurements? Do they get seen more often by their GP, right? And that's kind of collider bias that it's really hard to measure. So I think the negative control, when I review negative control outcomes, I want to make sure that they are definitely not caused by the treatment, because otherwise they wouldn't be a negative control outcome. But I do not mind having a few of them that do not entirely share the causal structure, because they give me additional information. So it's one of those where if you only measure ease and you don't look at the negative control outcomes, that's one way to go. And if you want to do a study like this with 100 databases and times 150 comparisons, maybe that's the only thing you can do, really. If you're doing a more traditional study where you have drug A versus drug B in 5 databases, potentially you can do these manually and still review them, right?
Perfect, thank you.
Well, we are at time. Thank you guys so much for being an active audience. I do believe there's lunch now for the next hour before the next set of sessions start. So again, please take everything with you. And thank you guys so much. I will be sharing an email later today with the PowerPoint, as well as some of the items that were discussed on the MS Teams chat.